Imagine looking up at the night sky, seeing those pinpricks of light, and thinking of the universe as something vast, silent, and almost frozen in time. It's a beautiful illusion, but the reality is so much more thrilling. Out there, in the deepest dark, celestial bodies are locked in a motion so grand and so precise it defies our everyday understanding of force and chaos. This is the story of an orbit so perfect, so mathematically elegant, that it didn't just nudge two galaxies, it brought them to their knees, reshaping their very structures and challenging everything we thought we knew about how the cosmos evolves. This isn't a destructive crash or a random act of violence. It's a gravitational ballet executed with impossible timing, a phenomenon that leaves even the most seasoned astronomers in awe of the universe's hidden order. We often picture space as a place of explosive collisions and random drift, but what happens when gravity doesn't just pull, it orchestrates? This precise orbit is one of those rare events where natural laws align like gears in a cosmic clock, governing the motion of hundreds of billions of stars, compressing gas clouds into stellar nurseries, and stretching dark matter into invisible scaffolds that guide the entire performance. You're about to dive into a celestial showdown where the usual rules don't apply, and where something as subtle as a repeated gravitational tug, applied with flawless rhythm, can alter the fate of entire galaxies over millions of years. This is where math meets majesty, and where we begin to see that the universe is less like a static painting and more like a living, breathing arena of dynamic force. Throughout this video, we'll unpack the forces behind this extraordinary event, how gravity, often called the weakest fundamental force, becomes an architect of transformation on a scale that humbles human imagination. You'll discover how orbits aren't just paths objects follow, but powerful tools that can compress time, warp space, and trigger creation and destruction in equal measure. By the end, you won't just see the night sky as a collection of distant lights. You'll sense the motion, the relationships, the influence of trajectories so exact they feel almost intentional. So settle in, open your mind, and get ready to rethink everything you thought you knew about movement, mass, and the silent power of a perfectly timed journey through the void. To truly grasp the magnitude of this event, we need to leave behind our earthly notions of time and space. Out in the cosmic ocean, two immense islands of light, each a majestic spiral galaxy, are navigating the profound emptiness. They are not hurtling directly toward one another in some violent, head-on collision. Instead, think of them as two enormous ships adrift on a current so slow it's almost imperceptible, their courses set by forces that began weaving their paths together billions of years ago. Each of these galaxies is a colossal metropolis of hundreds of billions of stars, with vast clouds of gas and dust swirling around a brilliant, dense core, all enveloped in an immense, invisible halo of dark matter that gives them most of their mass and gravitational influence. For most of their existence, they have been isolated universes unto themselves, living out their lives in splendid isolation, their stars being born, burning, and dying in cycles completely unaware of the other's existence. The initial conditions for their meeting are set by the expansion of the universe itself and the subtle, large-scale gravitational tugs from the cosmic web of matter that filaments throughout space. Their paths might appear random from our limited viewpoint, but in reality, they are the direct and calculable result of the distribution of mass around them. As the theoretical physicist Dr. Lisa Randall has often described, these galactic encounters are not mere accidents. They are fundamental experiments conducted on a grand scale. They are cosmic laboratories where the laws of physics play out with consequences that reveal the universe's deepest secrets, from the nature of the invisible dark matter that binds them to the intricate dynamics of how stars move and interact under immense gravitational stress. This approach is a slow, deliberate courtship governed by an unwavering set of physical rules. Over countless millennia, the gravitational field of one galaxy begins to gently pull on the stars and dark matter of the other. It's an incredibly soft touch across light years, a force so faint it would be undetectable to any local observer, but over astronomical timescales, it is utterly irresistible. This is not a chaotic crash. It is a meticulous, drawn-out gravitational dance where every movement is dictated by the precise mathematics of orbital mechanics. The galaxies begin to respond to each other's presence long before any noticeable distortion occurs, their mutual gravity ensuring their trajectories slowly curve toward a shared destiny. Watching this unfold is like observing the opening moves of a ballet performed over eons. The galaxies evolve from these isolated, serene islands into increasingly entangled partners, their fates becoming irrevocably intertwined. Their outer halos of dark matter are the first to make contact, merging and interacting long before their visible stars ever draw near. This initial, invisible handshake sets the stage for everything that follows, dictating the angle, the speed, and the ultimate precision of their orbital encounter. It is against this vast and patient backdrop that the stage is set for the orbital masterpiece to come, a phenomenon of such exquisite timing that it transforms a gentle gravitational nudge into a force capable of reshaping entire worlds. But what exactly do we mean when we call an orbit precise or perfect? In the cosmic sense, it has nothing to do with an abstract ideal of flawlessness. Out here, precision is a very specific, measurable quality. It's the relentless predictability of a path, the astonishing stability of a trajectory over timescales that dwarf human history. An orbit earns the title precise when its fundamental parameters resist the universe's constant tug toward disorder, maintaining their character for millions, even billions of years. This isn't a static state. It's a dynamic equilibrium where the relentless pull of gravity is perfectly countered by the object's momentum, creating a path of such consistency that its future position can be calculated with breathtaking accuracy. It is this unwavering reliability that allows even the gentlest of gravitational influences to build up, season after cosmic season, into a force of incredible transformative power. To understand this, we need to unpack the language of orbital mechanics, the mathematics of motion that governs everything from a satellite around Earth to a galaxy swinging past another. Every orbit has a set of defining characteristics, a cosmic fingerprint that describes its shape, tilt, and stability. The first is eccentricity, a number that tells us how circular or elongated the path is. An orbit with zero eccentricity is a perfect circle, while a highly eccentric one is a long, thin ellipse. In our galactic encounter, a precise orbit often has a low to moderate eccentricity. It's a smooth, repeating loop rather than a wild, slingshot trajectory that would only allow for a brief, disruptive encounter. Then there's inclination, the angle at which the orbit is tilted relative to a reference plane. A precise encounter often involves orbits that are coplanar or have very low inclination, meaning the galaxies are moving in the same general disk-like plane, allowing their gravitational forces to interact in a consistent, cumulative way, like two gears meshing smoothly instead of clashing at odd angles. Perhaps the most crucial property in this gravitational dance is something called angular momentum. In simple terms, you can think of it as the spin or the rotational inertia of the system. It's a measure of how much effort it would take to stop the orbiting object in its tracks. The beautiful thing about angular momentum is that, in the absence of outside forces, it is always conserved. It can't be created or destroyed, only transferred. This conservation is the bedrock of orbital precision. It acts as a cosmic gyroscope, providing a stabilizing force that keeps the orbit regular and resistant to collapse. It's the reason why, in our galactic duo, they don't just plummet directly into one another on their first approach. Their shared angular momentum forces them to miss each other, to swing around in a wide arc, setting the stage for a prolonged and intricate interaction rather than a single catastrophic event. The semi-major axis is another key player. It's essentially the average distance between the two interacting bodies, defining the size of the orbital track. In a stable, precise system, this distance remains remarkably constant over long periods. It's the metronome setting the pace for the entire gravitational waltz. When all these parameters, eccentricity, inclination, angular momentum, and semi-major axis align in a harmonious configuration, something special happens. The orbit enters a state of resonance. This is where the rhythmic gravitational tugs between the two objects sync up, reinforcing each other instead of fighting. It's the difference between randomly nudging a child on a swing and pushing at the exact peak of their arc every single time. Those perfectly timed pushes, small on their own, build into a massive, soaring motion. On a galactic scale, these resonant, precise orbits allow the gentle force of gravity to accumulate its effects over epoch after epoch, gradually transferring energy, stretching tidal tails, and compressing gas, orchestrating a chaos of stars into a new, ordered structure. As astrophysicist Neil deGrasse Tyson often articulates, this is how the universe writes its symphonies, not with a single, crashing chord, but with the patient, repeated application of a simple, precise theme that builds into something magnificent. Centuries ago, the night sky was a canvas of fixed points and mysterious, fuzzy patches. Astronomers like William Herschel, armed with the best telescopes of the 18th century, meticulously catalogued these nebulous objects. He noted that some appeared to be connected by faint bridges of light, a curious phenomenon he couldn't explain with the science of his day. To Herschel and his contemporaries, these were simply peculiar nebulae within our own Milky Way. The very idea that each could be an independent island universe of stars was a radical, even heretical, thought. Their early sketches, while beautifully detailed, depicted these connections as simple, static links, completely missing the dynamic, violent, and beautiful gravitational dance that was actually occurring. They were seeing the symptoms but had no framework to diagnose the cosmic disease. The true scale of the mystery began to unravel in the 1920s, thanks to the work of Edwin Hubble. Using the powerful new 100-inch Hooker telescope at Mount Wilson, he was able to resolve individual stars within the Andromeda Nebula by identifying a special class of stars called Cepheid variables, whose pulsating brightness acts as a reliable cosmic yardstick. Hubble made a staggering calculation. He determined that Andromeda was nearly 1 million light-years away, far too distant to be part of our own galaxy. In that single moment, the universe exploded in size. Those faint nebulae were not clouds within our Milky Way. They were galaxies in their own right, vast cities of stars separated by unimaginable gulfs of empty space. This revelation was the key that unlocked a new field of study. If these were independent galaxies, then their apparent interactions were not minor local events, but colossal encounters on the grandest possible stage. With this new understanding, the peculiar shapes and connections noted by earlier astronomers suddenly took on a dramatic new meaning. The stage was now set, but the actors were still blurry, and the script was written in a language no one could yet read. The next great leap came from the marriage of photography and spectroscopy. Long-exposure photographic plates, far more sensitive than the human eye, began to capture the faintest details of these interacting galaxies' delicate tidal tails, distorted spiral arms, and brilliant knots of light that hinted at ferocious bursts of new stars. But it was spectroscopy, the art of splitting light into its constituent colors, that gave these silent movies a soundtrack. By analyzing the spectra of these distant systems, astronomers could determine their composition, temperature, and most crucially, their motion. The Doppler shift, the same effect that makes a siren's pitch change as it races past, revealed that these galaxies were not only moving but moving at tremendous speeds. Spectra showed stars on one side of a galactic pair rushing toward us, blue-shifting their light, while stars on the other side were fleeing, their light redshifted. This was the smoking gun for rotation and orbital motion. It proved these systems were not static sculptures but dynamic, rotating entities caught in a gravitational embrace. Each technological advance, from larger mirrors that collected more light to more sensitive detectors, and eventually space-based telescopes free of Earth's blurring atmosphere, peeled back another layer of complexity. We moved from seeing simple, blurry smudges to mapping the detailed velocity structure of galactic encounters, watching the cosmic dance not as a single blurry frame, but as a slow-motion film where every star, every wisp of gas tells a part of the story. This entire journey of discovery stands as a powerful reminder that our modern insights, our sophisticated simulations of precise orbits, don't exist in a vacuum. They are built upon the patient, curious work of generations of observers who painstakingly mapped the heavens, each one adding a crucial piece to the puzzle, paving the way for us to finally understand the magnificent forces at play. So who are the lead dancers in this cosmic ballet? Let us introduce you properly to the pair known collectively as NGC 4676, but far more famously nicknamed the Mice. Located in the constellation Coma Berenices, these two spiral galaxies are caught in a gravitational embrace roughly 300 million light-years from Earth. That distance is almost impossible to fathom. The light we see from them today began its journey to our telescopes at a time when the first dinosaurs were just beginning to walk the Earth. And what we are witnessing is not a single, frozen snapshot, but an ongoing, dynamic process that has been unfolding for over 100 million years. They are a perfect example of interacting spirals, and their nickname comes from the two incredibly long, thin tails of stars and gas that stream out behind them, making the entire system look like a pair of mice scurrying through the void, connected by an invisible thread. While they are a pair, each galaxy has its own distinct personality and is responding to this gravitational tug of war in unique ways. The northern mouse, often designated NGC 4676A, is the one that appears to be leading the charge. It displays a classic, though now heavily disturbed, spiral structure. Its most striking feature is that spectacular tail, a luminous river of stars that has been stripped away and stretched out across space by the relentless gravitational pull of its partner. This isn't a trail of debris from a violent impact. It's a delicate filament, a testament to the precise and patient tidal forces at work, gently pulling stars from their original orbits and shepherding them into this new, elongated path. It's a cosmic signature, a direct piece of evidence recording the history of the interaction. Its partner, the southern mouse or NGC 4676b, tells a different part of the story. While it also sports a tail, its most dramatic response is happening within its own body. Observations, particularly in infrared and radio wavelengths, reveal furious bursts of star formation lighting up its core and spiral arms. This is because the gravitational forces of the encounter have done more than just pull. They have compressed. Vast clouds of interstellar gas and dust within the galaxy have been violently shaken and squeezed by the tidal forces. This compression increases the pressure and density in these clouds past a critical threshold, triggering the collapse of countless gaseous nurseries and igniting the birth of millions of new stars all at once. So while one galaxy is being pulled apart, the other is experiencing a ferocious wave of creation, a beautiful duality of destruction and rebirth happening simultaneously. To understand how this dance began, we need to consider their initial conditions. Both galaxies were likely once normal, barred spiral galaxies similar to our own Milky Way, each containing hundreds of billions of stars, vast clouds of gas and dust, and all enveloped in a massive, invisible halo of dark matter that makes up the bulk of their weight. They did not simply appear in each other's vicinity. Their paths were set by the larger gravitational landscape of the Coma Berenice's galaxy cluster, of which they are members. Their initial approach was not head-on, but a glide past each other at a specific angle and velocity, a near miss with profound consequences. This specific geometry, this first gentle gravitational handshake, is what determined the entire future of their interaction. It set the precise orbital parameters that would allow the tidal forces to build gradually rather than disrupt violently, making their encounter a masterclass in gravitational dynamics rather than a simple car crash in space. Astrophysicists like Dr. Michel Capillari study systems like the mice not just for their beauty, but because they are living laboratories. By measuring the motions of stars within each galaxy and along the tails, by mapping the regions of star formation, and by modeling their dark matter halos, researchers can reverse engineer the encounter. They can work backwards to determine the exact speeds, angles, and masses involved, testing our fundamental understanding of gravity itself. The mice, in all their splendor, are more than just celestial objects. They are a complex equation written across the sky, a key to unlocking the processes that have shaped galaxies throughout the history of the universe. Getting to know them as individuals with their distinct responses to a shared trauma transforms them from abstract points of light into characters in an epic story, deepening our awe for the incredible orbital precision that is directing their entire performance. It's a force so faint that here on Earth, the entire gravitational pull of an entire mountain can be overcome by a small refrigerator magnet, and yet across the light years, it becomes the ultimate architect of cosmic structure. Gravity's incredible weakness is its greatest strength on the grandest scales, because unlike the other fundamental forces that are either short-range or require specific charges, gravity's influence is cumulative, universal, and absolutely relentless. Every single atom, every star, every scrap of dark matter exerts its own tiny gravitational tug, and over the immense distances between galaxies, all those infinitesimal pulls add up into an irresistible shaping hand. This isn't a simple, crude force that just smashes things together like a wrecking ball. Instead, gravity is a master sculptor, an artist that works with the mediums of space and time to create intricate, beautiful, and often violent patterns across the cosmos. The true magic of gravity in this galactic dance isn't just its pull, but its gradient, the difference in its strength from one point to another. This is what creates the phenomenon of tidal forces. Imagine you're an astronaut floating near a black hole, falling in feet first. Your feet are slightly closer to the black hole than your head, so they feel a slightly stronger gravitational pull. This difference, however small, would begin to stretch you lengthwise. At the same time, your sides are all being pulled inward toward the center of the black hole, so you would also be compressed sideways. This simultaneous stretching and compressing is the essence of a tidal force. Now, scale this up from a single human to an entire galaxy made of hundreds of billions of stars. As our two galaxies draw near, the side of one galaxy facing its partner feels a stronger gravitational pull than the side facing away. This tidal force doesn't just move the whole galaxy. It actively distorts its very shape, pulling it apart and squeezing it in different directions, creating those spectacular, long tails of stars and triggering massive waves of star formation in compressed gas clouds. This incredible behavior is only possible because of a radical shift in our understanding of gravity itself, championed by Albert Einstein. Newton saw gravity as an instantaneous, mysterious force acting at a distance, but Einstein's theory of general relativity redefined it not as a force at all, but as a consequence of geometry. He proposed that mass and energy actually warp the very fabric of the universe, the four-dimensional combination of space and time. A massive object like a star or a galaxy sits in this cosmic fabric like a heavy bowling ball on a taut rubber sheet, creating a deep depression. The orbits we see are simply the paths that objects follow as they move through this warped landscape, like marbles rolling around the inner curve of the bowling ball's indent. The galaxies in our story aren't being pulled by invisible strings. They are each rolling through the curvature in space-time created by the other's immense mass. This warping is what makes an orbit possible, transforming a straight-line path through the universe into a curved, eternal dance. And this is where the true precision emerges from what might seem like chaos. The gravitational interaction between these two galaxies isn't a one-time event. It's a conversation that unfolds over millions of years. With each pass, each swing through their shared gravitational well, the effects are subtle. A few more stars are nudged from their original paths. A little more gas is funneled toward the center. A tidal tail grows infinitesimally longer. But because their orbit is so stable and predictable, these tiny nudges happen in the same direction, at the same point in the orbital cycle, over and over again. This is the power of resonance, the gravitational equivalent of pushing a child on a swing at the exact right moment every single time. The small, rhythmic inputs of energy build up into a massive, transformative outcome. The gentle tidal stretching on one pass amplifies the stretching on the next, allowing the galaxies to transfer energy and angular momentum between themselves with breathtaking efficiency. Visualize gravity in this context not as a brutal force, but as the most patient and precise conductor imaginable, standing before an orchestra of unimaginable size. It doesn't just wave a baton to make a loud noise. It cues each individual section, the strings of stars, the woodwinds of gas clouds, the percussion of dark matter, with impeccable timing. A slight gesture here brings in the tidal forces. A nod there emphasizes the compression. It understands the natural frequencies and rhythms of the entire system and uses them to build a symphony of motion from what would otherwise be random noise. Every single move in this grand performance, from the graceful sweep of a stellar stream to the violent burst of new stars, is orchestrated by this unseen hand, setting the stage for a dramatic finale that will forever alter the galaxy's destinies. To grasp the clockwork behind this celestial performance, we must first turn our attention to the foundational laws that govern all motion, from a falling apple to a galaxy in flight. Sir Isaac Newton's universal law of gravitation gave us the first mathematical language to describe the force pulling these cosmic partners together. His elegant equation states that every particle in the universe attracts every other particle with a force that is directly proportional to the product of their masses and inversely proportional to the square of the distance between them. In simpler terms, the bigger the objects and the closer they are, the stronger their gravitational pull. This inverse square law is the reason why gravity's influence weakens so dramatically with distance, yet its reach is truly infinite. For two galaxies, this means their mutual attraction is a complex sum of the pull between every single star, every gas cloud, and every bit of dark matter in one galaxy and every single bit in the other, a calculation of mind-boggling complexity. Newton's laws work perfectly for two isolated bodies, like a single planet orbiting a single star, a scenario masterfully described by Johannes Kepler's laws of planetary motion. Kepler gave us the shapes of orbits, ellipses with the central body at one focus, and the relationship between an orbit's size and the time it takes to complete. But our galactic dance is not a simple duet. It's a chaotic orchestra with hundreds of billions of participants. This is the infamous n-body problem, and it is fundamentally unsolvable with a single, neat equation. The gravitational pull on any one star comes not just from the other galaxy's core, but from every other star in both galaxies, a constantly shifting web of forces that makes predicting its exact path over long periods mathematically impossible in a straightforward way. This is where the concepts of stability and chaos enter the stage. The future of the entire system becomes exquisitely sensitive to the tiniest of changes in the starting conditions, a phenomenon often called the butterfly effect, but on a truly galactic scale. To navigate this complexity, astrophysicists rely on key simplifying parameters that act as a compass, giving them a statistical understanding of the system's overall behavior rather than the fate of any single star. One of the most crucial is the concept of reduced mass. When two bodies interact, you can mathematically transform the problem into one where a single, hypothetical object moves in the gravitational field of a fixed central point. This reduced mass captures the essence of the system's inertia, its resistance to change in motion. For our two galaxies, it's a way of treating their complex dance as if it were a single, simpler orbit, providing a bedrock understanding of their shared trajectory. Another vital parameter is their relative velocity. If this speed is too high, the galaxies will have a brief encounter, a gravitational slingshot that alters their paths but sends them flying apart again. If it's too low, they might plunge directly into a quick and messy merger. But if the relative velocity is just right, a Goldilocks zone of cosmic dynamics, it allows for the kind of gradual, resonant interaction that creates a long, drawn-out, and precise orbital dance. The true magic, the engine behind the precision, is a phenomenon known as orbital resonance. This occurs when the orbital periods of the two interacting bodies form a simple numerical ratio, like 2 to 1 or 3 to 2. Imagine pushing a child on a swing. If you push at random, inconsistent times, your efforts mostly cancel out, and the swing never gets very high. But if you push at the exact moment the swing reaches the peak of its arc and begins to fall, if your push is in resonance with the swing's natural frequency, then even the smallest push delivered rhythmically will build into a huge, soaring motion. On a galactic scale, this is exactly what happens. As the galaxies swing past each other, their gravitational tugs are not random. If their orbits are resonant, those tugs happen at the same point in each cycle. A little pull at the same relative position, over and over again for millions of years, allows the effects to accumulate constructively. This resonant interaction is what efficiently transfers energy and angular momentum from one galaxy to the other, what elongates the orbits, and what pulls out those magnificent tidal tails with such clean, precise geometry. It turns a gentle force into a transformative one. Given the mathematical intractability of billions of stars, how can we possibly hope to model and understand such a system? The answer lies in the power of modern computation. Astrophysicists use supercomputers to run what are called n-body simulations. They don't track every single star. That would be computationally impossible. But they use a few million or even billion particles to represent the entire stellar population and dark matter halo of each galaxy. Sophisticated codes calculate the gravitational force on each particle from every other particle at each tiny step forward in time, slowly building a movie of the interaction that unfolds over billions of years. Researchers can then play with the initial conditions, tweak the starting velocities, the angles of approach, the mass ratios. They run thousands of simulations to see which set of parameters produces a result that looks like the real galaxies we observe, like the mice. It's through this painstaking digital experimentation that we've learned how a fraction of a degree in the approach angle or a tiny percentage change in velocity can be the difference between a galaxy being shredded into a stream of stars or simply being gently stirred. These simulations reveal that the precision we witness is not a fluke or an accident. It is the direct, awe-inspiring result of specific, finely tuned physical laws playing out in a universe that is, at its heart, profoundly mathematical and predictable. Armed with the complex mathematics of orbital mechanics, but faced with the sheer impossibility of solving equations for hundreds of billions of stars, scientists had to find another way to witness this cosmic dance unfold. They built a universe inside a machine. This is the realm of computational astrophysics, where supercomputers perform the Herculean task of simulating galactic encounters, not with magic, but with millions of lines of code governing the laws of physics. The primary tool for this is something called an n-body simulation. The n stands for the number of particles in the system, and each particle isn't a single star. That would still be far too many, but rather a massive superstar that represents a collection of tens of thousands of actual stars, or a huge cloud of dark matter. The simulation assigns each of these particles properties like mass, position, and velocity, and then it sets the clock running. At each infinitesimal time step, the computer calculates the gravitational force that every single particle exerts on every other particle, then updates their positions and velocities accordingly. It's a process of mind-numbing repetition, requiring petaflops of processing power to simulate just a few million years of cosmic time. To make this colossal undertaking possible, researchers rely on sophisticated software frameworks. One of the most influential and widely used is a program called GADGET, which stands for Galaxies with Dark Matter and Gas Interact. Its second iteration, Gadget 2, became a workhorse for cosmologists worldwide. What makes such a code so powerful is its ability to handle not just the gravitational dynamics of dark matter and stars, but also the complex behavior of interstellar gas. This is crucial because gas responds to gravity in a different way. It can compress, heat up, radiate energy away, and form shock waves, all of which are critical for triggering the spectacular bursts of star formation we see in real collisions. Gadget 2 uses clever computational techniques to efficiently handle the vast range of scales involved, from the wide, empty spaces between galaxies down to the dense, collapsing cores of gas clouds where new stars are born. Pioneers in this field, like Dr. Volker Springel, who led the development of Gadget, have used these digital laboratories to run groundbreaking experiments. They start with two model galaxies, each with its own disk of stars and a large, diffuse halo of dark matter. They then set them on a collision course with specific initial conditions, a certain speed, a particular angle of approach. They press play, and the supercomputer grinds away for days or even weeks, simulating an event that takes 100 million years to unfold. By running thousands of these simulations with slightly different starting parameters, they can create a whole library of cosmic outcomes. Some encounters result in a quick and messy merger, others in a clean flyby that leaves both galaxies wounded but intact. and a special few with just the right combination of speed and trajectory result in the kind of precise, resonant interaction that produces beautifully symmetrical tidal tails and drives long-lasting, transformative change. The insights from this digital universe have been nothing short of revolutionary. Before simulations, the long, graceful tails seen in pairs like the mice were a profound mystery. Some theorized they were jets of material ejected from galactic centers, but simulations showed with stunning clarity that they are purely tidal phenomena, streams of stars and gas pulled out by gravitational forces, acting as a direct tracer of the orbital path itself. The simulations also predicted the existence of rare and beautiful ring galaxies, formed when a smaller galaxy plunges directly through the center of a larger disk galaxy. The gravitational shockwave from this bullseye impact propagates outward through the disk like a ripple in a pond, compressing gas and triggering a brilliant, expanding ring of star formation. This was a prediction made in silicon that was later confirmed by actual telescope observations. Perhaps the most humbling discovery from these models is the concept of a merger tree. Simulations of the entire universe's evolution, like the famous Millennium simulation, show that giant galaxies like our own Milky Way were not born whole. They are the products of a hierarchical history of cannibalism, built up over billions of years by digesting countless smaller dwarf galaxies. Each of those minor mergers was its own small-scale galactic encounter, governed by the same precise orbital rules. This means the majestic spiral we call home is the end product of a long and violent history of gravitational dances, a testament to the relentless, shaping power of orbits across cosmic time. By meticulously comparing the output of these simulations to the snapshots we get from our most powerful telescopes, we do more than just test a theory. We bridge the gap between the immutable laws of physics and the chaotic, beautiful reality of the universe we observe. These digital laboratories allow us to rewind the tape of cosmic history and play it forward again, giving us the front row seat to a show that takes 100 million years to perform, revealing the hidden precision behind what otherwise looks like celestial chaos. Now, as these two galaxies draw closer in their precise orbital dance, the true artist of this transformation steps into the spotlight, the tidal force. This is not a blunt, singular pull of gravity, but its subtle and relentless gradient, the difference in its strength from one side of a galaxy to the other. Imagine our own moon's gravity gently pulling on the Earth's oceans, creating the daily rhythm of high and low tides. Now scale that concept up by a factor of billions. Instead of a mere few feet of water rising and falling, we are talking about the gravitational pull from an entire galaxy, differentially tugging on every single star, every gas cloud, and every speck of dark matter in its partner. The side of a galaxy facing its approaching companion feels a significantly stronger gravitational pull than the side facing away. This difference, this cosmic stretching, is what begins to warp the very fabric of these colossal structures, pulling them out of their serene spiral symmetry and into new, distorted forms. The most visible and breathtaking signature of this process is the formation of immense tidal tails. These are not trails of destruction left behind from a violent impact. They are something far more elegant and precise. They are great rivers of stars, gas, and dust that are gently pulled away from their home galaxies by these differential forces. In a system like the mice, these tails can stretch for hundreds of thousands of light years, far longer than the parent galaxy itself. They act as a forensic record of the encounter, their length and curvature directly tracing the precise orbital path the galaxies have followed. The stars within these streams aren't being violently ejected. They are being shepherded, their orbits subtly altered by the tidal interaction until they find themselves flowing along these new, graceful trajectories through intergalactic space. It's a slow, patient process of gravitational sculpting that turns entire constellations into pliable clay, but the tidal force is a sculptor of two hands. While one hand is stretching and pulling matter outward to create these magnificent tails, the other hand is simultaneously compressing and squeezing. Just as the side of the galaxy facing its partner is being pulled outward, the sides perpendicular to that pull are being forced inward. This compression has a dramatic effect on the galaxy's vast reservoirs of interstellar gas and dust. These clouds, normally too diffuse to collapse under their own gravity, are suddenly and violently shaken. The tidal forces dramatically increase their density, pushing them past a critical threshold. This triggers a chain reaction of collapse, igniting ferocious waves of star formation. What was once a quiet, cold cloud of hydrogen can, in a cosmic instant, become a brilliant stellar nursery, giving birth to millions of new stars all at once in a spectacular burst of creation. So within the same galactic encounter, we witness this beautiful duality, destructive stretching on a grand scale and constructive compression on a local scale, both orchestrated by the same invisible force. The profound insights of astronomers like Dr. Francois Comez have shown us that these tidal interactions are about far more than just the visible stars and gas. They are, in fact, one of our most powerful tools for mapping the invisible. The way a visible galaxy warps and stretches under tidal forces doesn't just depend on the gravity of the stars we can see. It is overwhelmingly dominated by the gravitational pull of its massive, unseen dark matter halo. By carefully measuring the motions of stars within the tidal tails and the distorted disk, and by comparing those observations to sophisticated computer models, researchers can work backwards. They can essentially weigh the dark matter halo and chart its distribution. The very presence and shape of these magnificent tidal features are a direct testimony to the existence and dominance of dark matter. Without its immense gravitational scaffolding providing most of the mass, the tidal forces would be far weaker, and the spectacular streams we observe simply would not form. This is where the concept of a precise orbit elevates an interesting phenomenon into a transformative event. A chaotic, head-on collision would create a mess, a quick, violent shock that jumbles everything together. But a stable, resonant orbit allows the tidal forces to act with rhythm and purpose. Each time the galaxies swing past each other on their carefully tuned path, the tidal tug is applied at the same relative position. This resonant interaction amplifies the effect exponentially. A little stretch on one pass makes the galaxy slightly more vulnerable to stretching on the next pass. The gentle gravitational nudges build upon each other with metronomic consistency over millions of years, allowing the tidal forces to efficiently transfer energy and angular momentum between the two galaxies. This rhythmic, precise application of force is what allows the gentle tidal tug to ultimately overcome the immense self-gravity of an entire galaxy, patiently pulling it apart and reshaping its architecture into something entirely new, a permanent monument to the patient, mathematical power of gravity. And so we arrive at one of the most spectacular and beautiful consequences of this entire gravitational performance, a firestorm of creation. Amidst the chaos of stretching and distortion, the precise orbital dance triggers a phenomenal surge of new life, igniting stellar nurseries on a scale so vast it can redefine the very character of a galaxy. This isn't a slow, steady trickle of star birth. It's a veritable explosion, a starburst event that for a brief, brilliant period can outshine the rest of the galaxy combined. All that interstellar gas and dust that was once peacefully drifting through the spiral arms is suddenly and violently mobilized, becoming the raw fuel for a cosmic forge of unimaginable power. The same orbital precision that patiently pulls stars into tidal tails also acts as the ultimate matchmaker, compressing the ingredients for new suns and striking the spark that lights them aflame. To understand how this happens, we need to look at the life cycle of a star, which begins not with fire but with a chill. Deep within a quiet, isolated galaxy, vast molecular clouds drift enormous, frigid complexes of hydrogen gas and microscopic dust grains. These clouds are in a delicate equilibrium. Their immense mass creates a strong inward gravitational pull, trying to make them collapse. But this force is counteracted by several internal pressures: the thermal motion of the gas molecules, the turbulence of the cloud's internal currents, and the weak magnetic fields threading through it. For millions of years, this stalemate holds. The cloud may slowly, grudgingly form a few stars here and there, but it is mostly stable, a dormant reservoir of potential. It is waiting for a trigger, a catalyst powerful enough to upset this balance and tip the entire system into a frenzy of collapse. This is exactly what the precise orbital encounter provides, and it does so through the immense power of shock compression. As the two galaxies swing past each other, their gravitational fields don't just pull uniformly. They create powerful waves of pressure that surge through the interstellar medium, much like the bow wave that forms in front of a speedboat. Imagine taking a large, fluffy loaf of bread and suddenly squeezing it tightly in your hands. The air pockets collapse and the entire structure compacts into a dense lump. On a galactic scale, this is what occurs to those giant molecular clouds. The tidal forces and pressure waves generated by the gravitational interaction violently compress the gas, dramatically increasing its density by orders of magnitude in a relatively short cosmic time. This sudden compression is the critical trigger. By forcing the gas into a much smaller volume, the external pressure from the tidal forces overwhelms the cloud's internal supports. The thermal energy, the turbulence, and the magnetic fields can no longer hold back the relentless crush of gravity. The cloud fragments, with the densest knots at the center succumbing first. These knots, containing more mass than our entire solar system, begin to fall inward upon themselves. As they collapse, gravitational potential energy converts into heat, and the core temperature begins to skyrocket. When the core of one of these collapsing knots reaches a scorching 10 million degrees Kelvin, it crosses a fundamental threshold. Nuclear fusion ignites. A star is born, and in a starburst event, this isn't happening in one isolated location. It's happening simultaneously across vast swaths of the galaxy, turning entire spiral arms into a glittering tapestry of brilliant new suns. We can see this glorious aftermath clearly in our prime example, the mice galaxies. Optical telescopes show the familiar yellowish glow of older stars, but it's the view through infrared eyes that reveals the true spectacle. Instruments like those on the Spitzer Space Telescope can peer through the obscuring dust to see the thermal radiation from dust grains heated by countless newborn stars. In the southern galaxy, particularly in its core and along its distorted arms, the infrared signature is staggering. It reveals regions where stars are being formed at a rate hundreds of times greater than in a typical, quiet galaxy like our Milky Way. These are not just individual nurseries, they are sprawling megalopolises of star formation, vast clusters where massive, hot, blue stars ignite in rapid succession, flooding their surroundings with intense ultraviolet radiation that makes the surrounding gas clouds glow like magnificent neon signs. The work of astronomers like Dr. Deborah Elmergreen has been pivotal in helping us understand the long-term legacy of these violent births. she and others have shown that a starburst event is more than just a brief flash in the pan. It is an epoch that can define a galaxy's stellar population for the rest of its existence. The ferocious rate of star formation doesn't just produce sun-like stars. It creates a disproportionate number of very massive stars. These stellar behemoths live fast and die young, burning through their hydrogen fuel in only a few million years before exploding as spectacular supernovae. These explosions seed the galaxy with heavy elements, the oxygen we breathe, the carbon in our bodies, the iron in our blood, forging the essential building blocks for future planets and, potentially, life. The shockwaves from these supernovae can themselves trigger further rounds of star formation, creating a self-sustaining cycle of creation and destruction. The planetary systems that eventually form around the smaller, longer-lived stars will be richer in these metals, potentially altering the conditions for life itself. In this way, the orbital precision of a galactic encounter millions of years ago can set the stage for the chemistry of worlds that do not even exist yet, a testament to the deeply interconnected chain of cause and effect that weaves through cosmic history. This explosive surge of life, born from a dance of destruction, ensures that the legacy of the encounter is not one of empty ruin, but of a galaxy newly seeded with possibility, its future rewritten by the fires of its own rebirth. But for all the visible drama of colliding stars and igniting gas, we are still only witnessing the surface-level actors in this grand play. The true director, the hidden architect controlling every move from the shadows, is a substance that emits no light, reflects no radiation, and interacts with ordinary matter only through the faintest of gravitational whispers, dark matter. This enigmatic component makes up roughly 85% of all the matter in the universe, a staggering dominance that means the glittering spiral of stars we see in a galaxy is merely the decorative frosting on a colossal, invisible cake. The precise orbital dance we've been marveling at is not primarily choreographed by the gravitational pull of those hundreds of billions of suns. It is overwhelmingly orchestrated by the immense, unseen halo of dark matter that surrounds each galaxy, a halo that extends far beyond the visible edge and contains up to 10 times more mass than everything we can actually see. This dark matter halo is the fundamental gravitational scaffolding upon which the visible galaxy is built. It acts as a vast, deep well of gravity that governs the motion of everything within it. When two galaxies like the mice begin their approach, it is not their sparkling disks that first make contact. It is these enormous, overlapping halos of dark matter. Long before any stars are distorted or any gas clouds are compressed, these invisible giants are already shaking hands in the dark, their gravitational fields intertwining and setting the rules of engagement. The trajectory of the encounter, the very stability and precision of the orbit itself, is largely predetermined by the mass, size, and distribution of these dark matter halos. A massive, extended halo will exert a far stronger gravitational pull, increasing the chances of capturing an incoming galaxy into a bound orbit that leads to an eventual merger. A less massive halo might allow a galaxy to make a single, dramatic pass and then escape back into the void, forever altered but not bound. The fate of the entire visible system hinges on the properties of the invisible one. So how can we possibly study something we cannot see? Astronomers are like cosmic detectives, and they have two brilliant methods for mapping this invisible mass. The first relies on a prediction from Einstein's theory of general relativity. That mass warps the fabric of space-time and consequently the path of light itself. This phenomenon is called gravitational lensing. When the light from a very distant galaxy passes near a massive foreground object, like a cluster of galaxies, the immense gravity of that foreground mass, dominated by its dark matter, acts like a lens, bending and distorting the background light. By meticulously studying the pattern of these distortions, astronomers can create a detailed mass map of the foreground object. They can literally trace the distribution of the gravity, and since visible matter doesn't provide nearly enough, they can pinpoint exactly where the dark matter must be, revealing its intricate structure and revealing these vast halos that extend far into the intergalactic void. The second, more historical method involves watching how visible objects move under the influence of the invisible gravity well. This was the pioneering work of the late, great astronomer Dr. Vera Rubin in the 1970s. She meticulously measured the rotation curves of spiral galaxies, plotting how fast stars and gas clouds orbit the galactic center at different distances. According to Kepler's laws, stars on the outer edges of a galaxy, far from the central bulge of mass, should orbit much more slowly, just as Pluto crawls around the Sun compared to the zipping inner planets. But Rubin's data revealed something astonishing and universe-changing. The orbital speeds of these outer stars did not drop off. They remained high, flatlining out to the very edges of observation. This could mean only one thing. There had to be a tremendous amount of unseen mass far beyond the visible disk, providing the extra gravitational grip to keep those stars whirling around at such incredible speeds. Her work provided some of the strongest early evidence for dark matter, and as she famously stated, it revealed a universe where what we see is not what we get. It's very clear that for a large part of the universe, the light is not a good tracer of the mass, she noted, highlighting the profound disconnect between the visible cosmos and its true, hidden structure. When we apply this understanding back to our galactic encounter, the entire event snaps into a new, sharper focus. The beautiful, precise orbit is not just a path between two collections of stars. It is a pathway carved through the combined, deep gravitational landscape of two overlapping dark matter halos. The visible tidal tails and starburst regions are merely the luminous tracers, the glowing footprints, showing us where the invisible mass has guided and compressed the ordinary matter. The stability of the orbit, its resonant quality that allows effects to build over millions of years, is a direct consequence of the smooth, extensive gravitational field provided by the dark matter. It provides a stable framework that prevents the encounter from simply dissolving into a chaotic mess. This realization deepens the mystery and the majesty of what we are witnessing immensely. We are not just watching two galaxies interact. We are seeing the visible manifestation of a hidden architecture, a cosmic dance where the primary partners are invisible, and the stars are just along for the ride, lighting up the stage so we can finally begin to see the true directors of the universal ballet. To truly appreciate the breathtaking precision of this orbital dance, we must first warp our sense of time, trading our human-scale seconds for the universe's deep geological epochs. This is not a story that unfolds in years or even millennia, but in units of time so vast they defy easy comprehension. The entire performance, from the first faint gravitational whisper to its stunning finale, spans well over 100 million years, a duration in which entire mountain ranges can rise and erode away on distant worlds, and species can evolve and go extinct a dozen times over on our own. The encounter between our two galactic protagonists is a cosmic epic in three distinct acts, a slow-motion ballet where every pirouette and lift takes millions of years to execute, and the climax is a transformative event that forever alters the identities of the dancers themselves. The first act begins not with a dramatic crash, but with an almost imperceptible drift. For countless millions of years, the two galaxies have been sailing through the void on their own independent courses, their paths set by the large-scale flow of the cosmic web. The initial approach is so slow, so gradual, that if you could somehow speed up time to watch it, it would appear as if two immense, glittering clouds were being drawn together by an invisible, inevitable current. This is the distant passage phase. The galaxies are still far apart, perhaps hundreds of thousands of light years separating their visible disks, but their immense, overlapping halos of dark matter have already made first contact. This is the unseen handshake that sets the rules of the dance, their combined gravitational fields beginning to gently curve each other's trajectories. From our perspective, this phase is one of mounting anticipation, a cosmic prelude where the forces are aligning for the main event, yet the visible changes are still subtle, a slight shimmer of distortion at the very outermost edges of their spiral arms. Then comes the moment of closest approach, the second act and the heart of the entire performance. This is not a single, instantaneous event, but a prolonged and intense period of gravitational interaction that can last for tens of millions of years. As the galaxies swing past each other, their relative speeds are staggering hundreds of kilometers per second, yet their immense size means this pass is still a graceful, drawn-out arc. This is the point where the tidal forces we discussed earlier reach their absolute peak. It is during this close passage that the gravitational differential between the near and far sides of each galaxy becomes most extreme. This is when the long, elegant tidal tails are truly born, pulled out from their parent galaxies like cosmic taffy, their stars and gas streaming into intergalactic space, tracing the precise orbital path for all to see. Simultaneously, the immense shockwaves of pressure slam through the galaxy's gas clouds, triggering the ferocious starbursts that light up their cores and arms in a brilliant firestorm of new suns. This is the climactic moment of maximum stress and maximum beauty, where the orbital precision pays off in a spectacular display of gravitational sculpting. What happens next in the third act is where the initial orbital parameters, the speed, the angle, the mass, write the final chapter. The galaxies, having exchanged energy and momentum during their close encounter, now have two possible fates. In one scenario, they had just enough relative velocity to overcome their mutual gravitational pull. They swing past each other, forever altered, and continue on into the void, now flying apart on new, separate trajectories. They become what astronomers call a fly-by interaction, two wounded but independent galaxies carrying the spectacular scars of their encounter, long tails of exiled stars and a legacy of new stellar generations. In the other, more dramatic outcome, their orbit was just slow and tight enough. The encounter robs them of the kinetic energy needed to escape. They don't fly apart. Instead, they fall back toward each other, pulled by the relentless grip of gravity. This begins the long, slow process of a full merger, a series of ever closer passes where they swing around each other in a decaying orbit, each pass pulling them tighter together, further distorting their shapes, and eventually erasing their individual identities to forge an entirely new, blended galaxy, most likely a giant elliptical. Researchers like Dr. John Dubinsky have used incredibly sophisticated computer simulations to visualize this entire timeline, creating movies that compress 100 million years into a few mesmerizing seconds. His work, and that of others in the field, shows with stunning clarity how the slightest change in the initial conditions, a fraction of a degree in the angle, a tiny percentage difference in the speed, can completely alter the entire story, leading to either a fleeting encounter or a total merger. Watching these simulations is a humbling experience. It forces us to confront the sheer patience of the cosmos, where a single orbit's flawless geometry is not a quick event but a sustained force that builds its effects with metronomic consistency over epochs. This timeline isn't just a sequence of events, it is a testament to the power of precision, a demonstration that in the grand theater of the universe, the most transformative dramas are not the loud, explosive crashes, but the patient, rhythmic dances that build their power over millions of years, culminating in a climax that reshapes the very architecture of reality. To grasp the true engine behind this cosmic transformation, we need to follow the flow of energy itself, the fundamental currency that powers every twist and turn in this gravitational waltz. Just like a child on a swing who soars highest at the ends of their arc and moves fastest at the bottom, our two galaxies are engaged in a constant, elegant trade-off between two fundamental forms of energy. The first is kinetic energy, the raw energy of motion, the sheer velocity that propels them through the void. The second is potential energy, which is a bit more abstract. It's the stored energy an object possesses because of its position within a gravitational field. Think of it like this: a rock held high in the air has a lot of gravitational potential energy. Drop it, and that potential energy is converted into the kinetic energy of its fall. In our galactic dance, the same principle applies on an unimaginable scale. As the galaxies fall toward each other, drawn by their mutual gravity, their potential energy is converted into the kinetic energy of their ever-increasing speed. Then, as they reach their closest point and begin to swing away, that kinetic energy is converted back into potential energy, slowing their ascent like a ball tossed into the sky, gradually losing speed. This continuous, rhythmic exchange is the heartbeat of the entire encounter. This cosmic energy trade is governed by one of the most fundamental and beautiful laws of physics, the conservation of energy. Energy cannot be created or destroyed. It can only change form or be transferred from one object to another. In a simple, two-body system like a planet orbiting a star, this exchange is perfectly balanced, leading to a stable, repeating elliptical orbit. But our galactic duo is far from a simple system. They are messy, complex collections of billions of stars and vast clouds of gas, all interacting at once. Energy isn't just sloshing back and forth between the two galaxies as single entities. It's being transferred between countless individual components within them. Stars can gain or lose orbital energy through gravitational interactions, effectively acting as a way for kinetic energy to be transferred from one part of the system to another. This internal shuffling of energy is crucial because it determines the ultimate fate of the entire pair. This is where the concept of a precision orbit becomes so powerful. A chaotic, head-on collision would be a terribly inefficient way to transfer energy. It would be like trying to slow down a speeding car by crashing it into a wall. Most of the energy is dissipated violently as heat, sound, and deformation. But a precise, resonant orbit is like a skilled driver gently applying the brakes over a long distance. It allows for a smooth, gradual, and incredibly efficient transfer of energy, and just as importantly, angular momentum from one galaxy to the other. With each graceful pass, the rhythmic gravitational tugs act like a pump, systematically moving energy from the orbital motion of the pair into the internal motion of the stars within each galaxy. This process slowly robs the system of the kinetic energy it needs to fly apart, effectively applying a gravitational brake. The overall stability of this complex, evolving system is elegantly described by a key principle in physics known as the virial theorem. Don't let the name intimidate you. The concept is profoundly insightful. In simple terms, for a system that is in a stable, gravitationally bound configuration, like a star cluster, a galaxy, or even our interacting pair, the virial theorem states that the total kinetic energy of all the moving parts is balanced by about half of the total gravitational potential energy, but with an opposite sign. It's a cosmic balancing act that ensures the system doesn't either fly apart or collapse in on itself. When the galaxies first approach, they are not necessarily in this virial equilibrium. The gravitational interaction itself, especially if it's precise and resonant, acts to push the system toward this stable state. As energy is transferred and redistributed, the entire duo settles into a more relaxed, bound configuration. This theorem is the mathematical expression of the stability we see in so many celestial objects, the hidden order within the apparent chaos. The renowned physicist Richard Feynman once marveled at this universal principle, noting that there is a fact, or if you wish, a law, governing all natural phenomena that are known to date. There is no known exception to this law. It is exact so far as we know. The law is called the conservation of energy. He described it not as a description of a mechanism, but as a profound statement about nature's bookkeeping. The total numerical quantity of energy in the universe remains constant, even as it constantly changes form. Watching this law play out on a galactic scale is to witness this cosmic accounting in its most grand and dramatic form. The kinetic energy of a galaxy's approach is never lost. It is transformed into the heat of new stars, the brilliant light of supernova, and the gravitational potential energy that ultimately binds the two galaxies together, forging a single new entity from what were once two separate islands in the void. Witnessing the morphological transformation of a galaxy is like watching a master sculptor at work, but instead of chisels and clay, the tools are gravity and time, and the scale is almost beyond comprehension. We are not looking at static portraits hung in a cosmic gallery. We are observing dynamic, evolving entities in a state of constant flux, reshaped by the relentless gravitational tides of a precise orbital encounter. The familiar, majestic pinwheel of a spiral galaxy, with its graceful arms winding out from a bright core, is an illusion of stability. It is a temporary configuration, a single frame in a movie that lasts billions of years, and a close gravitational pass from another galaxy is the directorial cue for a dramatic change of scene, rewriting the very form and function of these stellar cities. The first and most obvious casualty of this encounter is the delicate symmetry of the spiral arms themselves. These arms are not solid structures but density waves, patterns of compressed gas and stars that move through the galactic disk like a traffic jam on a circular highway. The gravitational pull from an intruding galaxy acts as a massive perturbation, violently disrupting this orderly wave pattern. The arms don't just bend, they are pulled, stretched, and sheared into entirely new configurations. On the side of the galaxy closest to the intruder, the pull is strongest, dragging material outward to form the spectacular tidal tails we see in the mice, those luminous rivers of exiled stars. On the opposite side, the weaker gravitational pull can actually create a countertail or warp the entire disk into a pronounced, lopsided asymmetry. The galaxy begins to lose its pristine, two-dimensional disk-like quality, its structure becoming increasingly three-dimensional and chaotic as the encounter progresses. Simultaneously, a profound transformation is often taking place deep within the galaxy's heart, the formation and enhancement of a central bulge. Imagine the galactic disk as a vast, flat whirlpool of stars. The gravitational shock of the encounter sends powerful ripples, density waves racing inward through this whirlpool toward the center. Just as ocean waves pile up water onto a beach, these waves deliver a massive influx of stars and gas toward the galactic core. This inward migration of material rapidly builds up the central bulge, fattening it and making it more prominent. In some cases, if the conditions are just right, This process can even trigger the formation of a bar, a straight, elongated structure of stars that cuts through the center of the galaxy, connecting the inner ends of the spiral arms. This bar acts as a cosmic pipeline, funneling even more gas and dust directly into the very center, feeding the supermassive black hole that likely resides there and potentially igniting it as a brilliant active galactic nucleus. The galaxy's serene center becomes a crowded, bustling metropolis, its gravity well deepened by the influx of new mass. The elegant, thin disk of the galaxy also undergoes a radical thickening process. Before the encounter, stars orbit in relatively flat, circular paths, like marbles rolling on a smooth tabletop. The gravitational perturbation from the passing galaxy gives these stars energetic kicks, tilting their orbits and making them more elliptical and inclined. This is the thermodynamic equivalent of heating a gas. The random motions of the stars increase, causing the entire disk to puff up. It loses its razor-thin profile and becomes a thicker, hotter, more disordered system. This process, which astronomers call heating the disk, is a one-way street. It is incredibly difficult to cool a galactic disk back down and return it to its pristine, thin state. This transformation marks a fundamental and irreversible evolutionary step, pushing the galaxy from an ordered, rotating spiral toward a more chaotic, pressure-supported structure, like an elliptical galaxy. The pioneering work of astronomers like Dr. Alar Toomer and his brother Jory in the 1970s was instrumental in creating a classification system for these morphological changes. Through their influential simulations, they showed how different types of galactic encounters, varying the mass ratio, the impact parameter, and the orbital inclination, could produce a stunning variety of outcomes. They could create everything from beautiful ring galaxies to spectacular antennae-like systems with dual tails, and ultimately, to the complete erasure of all disk structure in a merger, resulting in a featureless elliptical galaxy. Their research provided the crucial link, demonstrating that the final form of a galaxy is not predetermined at birth, but is a direct consequence of its interaction history and the precise orbital parameters of its gravitational encounters. A galaxy's shape is a living record of its past relationships. This constant state of cosmic reinvention forces us to abandon any notion of galaxies as isolated, immutable islands. They are instead dynamic and social entities, their structures forged and continually remade through a history of gravitational interactions. A precise orbit is the ultimate catalyst for this change. It doesn't simply cause a brief disruption. It provides the sustained, rhythmic forcing needed to efficiently transfer energy and angular momentum to drive the internal transformations, the buckling of disks, the growth of bulges, the fueling of black holes that permanently alter a galaxy's identity. The majestic spiral we see today may be the temporary result of a long ago, gentle flyby, while the giant elliptical galaxy at the heart of a cluster could be the final product of a violent, ancient merger, its individual history completely erased, a monolithic monument to a dramatic and precise dance that brought its progenitors to their knees. But the drama doesn't end with their formation. A supermassive black hole binary is a system with a finite lifetime, destined for one of the most violent and energetic events in the entire cosmos, a merger. As these two incomprehensibly dense objects spiral ever closer, they lose energy by rippling the very fabric of the universe itself. They emit gravitational waves propagating distortions in spacetime predicted by Einstein's theory of general relativity. This emission is a slow process at first, but as the black holes get closer and their orbital speed increases, the energy loss accelerates, culminating in a final, furious in-spiral. The final moments before merger would be a spectacle of almost unimaginable power. For a brief instant, the binary would pump out more energy in gravitational waves than all the stars in the observable universe combined, sending a permanent ripple through the cosmos that, if we were close enough, would stretch and compress everything in its path, including the space we occupy. The monumental work of astronomers like Dr. Andrea Ghez, who was awarded a Nobel Prize for her precise measurements of the stars orbiting our own galaxy's central black hole, Sagittarius A, gives us a profound understanding of their gravitational dominance. Her decades-long study of individual stars whipping around the galactic center at thousands of kilometers per second provides the most direct and compelling evidence for the existence of these supermassive objects. Measuring the orbits of stars at the center of our galaxy, she has explained, is like watching a distant ballet where the dancers are moving to the music of an invisible, immensely powerful conductor. Her work translates the subtle motions of distant suns into a precise measurement of the black hole's mass, confirming its overwhelming gravitational influence over its immediate surroundings, and proving that these cosmic engines are not theoretical curiosities but fundamental components of galactic architecture. When we zoom back out to the scale of our interacting galaxies, we see that the orbital precision governing the entire encounter trickles all the way down to these darkest of hearts. The same resonant, stable orbit that allows the galaxies to transfer energy and form tidal tails also provides the perfect conditions to align the orbits of their central black holes, guiding them toward their eventual binary formation and merger. This creates a beautiful and profound symmetry across scales. A precise galactic orbit, measured in hundreds of thousands of light years, ultimately dictates the fate of objects separated by mere light hours, orchestrating a dance that concludes with a flash of energy that resonates across the space-time continuum. The supermassive black holes are not passive prisoners of this process. They are active participants, their own gravitational might feeding back into the system, influencing the flow of gas, the rhythm of star birth, and the final morphological structure of the new galaxy they will one day call home, a testament to the interconnected nature of cosmic forces from the largest scales down to most infinitesimal. While stars are the glittering actors on this cosmic stage and dark matter the unseen director, it is the interstellar gas that serves as the raw fuel, the lifeblood of galactic evolution. This primordial hydrogen, mixed with traces of helium and dust, is the quiet, invisible medium that fills the vast spaces between the stars. In a solitary, undisturbed galaxy, this gas drifts in a relatively calm equilibrium, but when two galaxies engage in their precise orbital dance, this placid reservoir is violently mobilized, becoming the key ingredient in a transformative alchemy that can birth new suns and feed ravenous black holes. The way this gas responds to the gravitational tides is utterly different from the behavior of stars or dark matter. It is a fluid, and it flows, and that flow is channeled with astonishing precision by the geometry of the orbit itself, creating shock waves and compression fronts that become the engines of cosmic change. As the galaxies swing past each other, their gravitational forces don't just pull on the gas, they sculpt it. The precise, repeating nature of a resonant orbit acts like a cosmic plow, funneling vast rivers of hydrogen along specific trajectories. This isn't a random splashing, it's a directed flow. The gas gets channeled into spectacular bridges that stretch between the two galaxies, into immense ring structures that can encircle an entire galactic core, and into dense, turbulent streams that flow inward toward the central supermassive black holes. We can actually observe these structures using radio telescopes, like the mighty Atacama Large Millimeter Array, or ALMA, which is specially tuned to detect the faint radio whispers emitted by cold molecular hydrogen. These observations reveal a universe crisscrossed by these delicate filaments and ribbons of gas, each one a direct map of the gravitational forces and the orbital path that created it. They are the luminous traces of the invisible architecture, showing us where the cosmic rivers are flowing. The consequences of this directed flow are dramatic. When these fast-moving streams of gas collide with slower-moving material already within a galaxy, or when streams from opposite sides of a galactic collision slam into each other, they create immense shock waves. Think of it like two powerful fire hoses aimed directly at each other. At the point of impact, the water is violently compressed and forced outward. On a galactic scale, this collision of gaseous streams creates regions of extreme pressure and density. This sudden compression is the primary trigger for the starbursts we discussed earlier. It forces countless diffuse hydrogen clouds to collapse all at once, igniting the furious birth of millions of new stars in brilliant, localized firestorms that can outshine the rest of the galaxy. The orbit, through its precise channeling of gas, literally dictates the location and timing of these stellar nurseries, painting bursts of new light onto the galactic canvas. But not all of this funneled gas ends up forming stars. A significant portion of it, particularly the material channeled directly toward the galactic centers, has a very different destiny. It becomes food for the supermassive black holes lurking there. As these vast rivers of gas flow inward, they don't fall in directly. Conservation of angular momentum forces them to spiral inward, forming a furious, hot accretion disk around the black hole. Friction within this whirling disk heats the gas to millions of degrees, causing it to glow with intense X-rays before it finally crosses the event horizon and vanishes. This process can transform a dormant black hole into an active galactic nucleus, one of the most energetic phenomena in the universe, blazing with the power of 1 trillion stars. The precision of the galactic orbit is what opens this pipeline, determining how much fuel is delivered and thus how brightly the central engine will shine. Leading this fascinating field of research is astrophysicist Dr. Lisa Cooley, whose work focuses on connecting these grand-scale gas dynamics to the chemical evolution of galaxies. Her team uses sophisticated models to track how these shock waves and compression fronts not only form stars but also forge heavy elements. The violent death of massive stars born in these starbursts enriches the surrounding gas with oxygen, carbon, and iron, the very elements essential for planets and life. As Dr. Cooley has illustrated, this isn't just a mechanical process, it's a chemical one. The galactic encounter, guided by its precise orbit, doesn't just reshape the galaxy's structure, it fundamentally alters its chemical composition, seeding it with the raw materials for future planetary systems and potentially setting the stage for biology billions of years in the future. To visualize this complex process, imagine a massive, slow-moving river on Earth, like the Colorado River carving through the Grand Canyon. The river's path is its orbit, determined by the landscape's gravity. Over eons, this persistent, precise flow excavates rock, sculpting the canyon into a deep, dramatic channel. In our galactic encounter, the orbital path is the riverbed, and the interstellar gas is the water. The gravitational tides act as the flowing current, relentlessly carving channels through the galactic medium, concentrating the gas into specific, deep streams. And just as sediment is deposited in a river delta, building new land, the compressed gas at the end of these cosmic rivers collapses to build new stars and solar systems. This dynamic interplay reveals the true depth of orbital precision. It's not a force that only guides the motion of large objects. It's a master regulator that orchestrates the flow of the very fuel that drives a galaxy's growth, its energy output, and its ultimate transformation from a simple collection of stars into a complex, evolving ecosystem. And just as a river in flood leaves behind silt and sandbanks that chart its course long after the waters have receded, so too does this galactic encounter leave behind permanent evidence of its precise orbital path. We've seen how tidal forces pull and stretch, but their most enduring legacy is not the grand distortion of the galaxies themselves, but the delicate, luminous trails of stars they leave strewn across the intergalactic void. These are the stellar streams, and they are far more than just beautiful accidents. They are the ultimate forensic record of the encounter, a cosmic breadcrumb trail that allows us to rewind time and reconstruct the entire gravitational dance with astonishing accuracy. In a very real sense, these streams are the orbit made visible, a glowing signature written in stars against the blackness of space. The process of their creation is one of gentle theft, not violent expulsion. As the two galaxies perform their gravitational waltz, a star orbiting in the outer disk of one finds itself in a celestial tug of war. The gravitational pull from its own galaxy is competing with the pull from the intruder. For stars in the inner regions, the home galaxy's grip is too strong to break. But for those in the sparse outer reaches, the external tug can be just enough to tip the balance. These stars aren't ripped away in a single dramatic event. Their orbits are simply perturbed, nudged onto new trajectories that slowly, over millions of years, carry them away from their parent galaxy. Because this process is driven by the smooth, rhythmic tidal forces of a precise orbit, the escaping stars don't fly off randomly, they are shepherded. They leave in a coherent group, their path still eerily similar, forming a long, coherent stream that almost perfectly traces the orbital route the two galaxies have taken. It's a testament to the order within the chaos. Even as gravity pulls the galaxy apart, it does so with a geometric precision that creates these elegant, linear structures. Now look back at our prime example, the mice galaxies. Their most stunning feature are those two magnificent, opposing tails. For a long time, their true nature was a mystery. But we now understand that these are not jets or ejected material. They are the quintessential stellar streams, each one a river of millions of suns that has been pulled out from its host. The fact that there are two distinct, long, and relatively thin tails is itself a powerful clue. It tells us that the encounter was not a direct hit, but a very specific, clean flyby that allowed the tidal forces to act symmetrically and efficiently. The very existence, length, and shape of these streams are the first pieces of data in our cosmic reconstruction, but the forensic analysis goes much, much deeper. Astronomers like Dr. Katherine Johnston of Columbia University have pioneered the use of these streams as the most sensitive scales in the universe for weighing dark matter. Her work has shown that the stars within a stream continue to move along their orchestrated path, held in the gravitational grip of the galaxy's extensive dark matter halo. If the dark matter halo were smooth and spherical, the stream would form a nearly perfect narrow line. But if the halo is lumpy or has a more complex shape, perhaps because it's been disturbed by smaller, previously ingested dwarf galaxies, that subtle substructure will gravitationally perturb the stream. It will cause kinks, gaps, or even shearing within the stellar river. As Dr. Johnston has explained, stellar streams are like celestial ribbon. The way they are woven and torn tells us about the invisible hand that is weaving them, the hand of dark matter. By meticulously mapping the finest details of a stream's morphology, astronomers can literally chart the distribution of the invisible dark matter that dictated its form, turning a luminous trail into a three-dimensional map of the unseen. Furthermore, the stars within the stream are not anonymous prisoners. They are individuals with stories to tell. Using powerful spectrographs, astronomers can measure the velocity of each star along the line of sight. This reveals an even more stunning pattern. The stars at the very tip of the stream are moving at a different speed than the stars closer to the parent galaxy. This velocity gradient is the smoking gun of orbital dynamics. It confirms that the entire stream is a snapshot of a single, stretched-out orbital period, with different stars frozen at different points along the same gigantic path. By analyzing these motions, researchers can work backwards with gravitational equations to determine the exact mass of the host galaxy, the original orbital parameters of the encounter, and even the precise timing of when the stream began to form. It's a level of detail that transforms a pretty picture into a quantitative data set of immense power. These stellar fingerprints thus reveal a layered history, a story of both loss and creation. They tell a tale of gravitational theft, of stars stolen from their birthplace and sent on a permanent exile into the intergalactic wilderness. But they also whisper a story of creation, for the same precise orbit that pulled them out also compressed gas to form new generations of stars back in the galactic core. The streams are a permanent monument to the encounter, and their longevity is key. Unlike the brilliant but short-lived firestorm of a starburst, these streams will persist for billions of years, long after the parent galaxies have fully merged or flown apart. They will hang in space as ghostly reminders of a dramatic event that unfolded in the distant past, a fossil record of a single, perfect orbit that once brought two mighty galaxies to their knees, forever etching its path in the scattered light of a billion stolen suns. Now we arrive at the secret weapon in gravity's arsenal, the hidden amplifier that turns a gentle nudge into a transformative shove, resonance. This isn't just a scientific term, it's a universal principle, a phenomenon where timing is everything. We experience it in our everyday lives. Think about that child on a swing again. If you push at random, inconsistent intervals, your efforts mostly cancel out. But if you push at the exact moment the swing is at its peak and beginning to fall, if you push in rhythm with its natural frequency, the smallest, most gentle pushes will build into a huge, soaring arc. You are in resonance with the swing, and you are amplifying its motion with breathtaking efficiency. Now, transpose that concept from a backyard swing set to a gravitational dance between two galaxies, where each push is a gravitational tug separated by millions of years, and you begin to grasp the awesome, patient power of orbital resonance. In the context of our galactic encounter, orbital resonance occurs when the orbital periods of the two galaxies, or of structures within them, form a simple integer ratio. This means their gravitational interactions happen at the same relative point in their paths over and over again. It's the difference between a drummer hitting a drum at random and a drummer keeping perfect metronomic time. The rhythmic drummer, the one in resonance, can drive the entire band. When two galaxies have orbits that are in, say, a 2-to-1 resonance, it means that for every two orbits one galaxy completes, the other completes exactly one. Every time they reach that specific alignment, one galaxy gives the other a gravitational kick in the same direction at the same point in space. These kicks are small on their own, but because they are applied rhythmically and constructively, they don't cancel out. Instead, they build, they accumulate. Over millions of years, this resonant forcing can pump a tremendous amount of energy into the system, dramatically increasing the eccentricity of the orbits, elongating them, and making the tidal forces far more effective at pulling the galaxies apart. To understand how this shapes a single galaxy, we can look to the work of pioneers like Dr. Frank Hsu, who elegantly explained how resonances sculpt the beautiful spiral arms we so admire. Within a rotating galaxy, stars and gas clouds orbit the center at different speeds depending on their distance. This is called differential rotation. Dr. Xu and others showed that spiral arms aren't permanent structures made of the same stars, but are actually density waves, patterns of compressed material that move through the galactic disk like a traffic jam on a circular freeway. Orbital resonances are the engines that create and sustain these patterns. A key player is the Lindblad resonance, named after the Swedish astronomer Bertil Lindblad. This occurs at the specific distance from the galactic center where the orbital frequency of a star matches the frequency of the passing spiral wave. Stars at these resonant points receive a steady, rhythmic gravitational nudge from the wave itself, which organizes their orbits and helps to reinforce the very pattern that is nudging them. It's a beautiful, self-sustaining feedback loop where the wave creates the resonance and the resonance sustains the wave, all driven by the impeccable timing of orbital mechanics. We can see a stunning example of resonance right here in our own solar system with the moons of Jupiter. The innermost large moon, Io, is in a precise orbital resonance with its neighbors Europa and Ganymede. For every one orbit that Ganymede completes, Europa completes exactly 2, and Io completes exactly 4. This 1 to 2 to 4 resonance has profound consequences. The repeated, rhythmic gravitational tugs from its sister moons prevent Io's orbit from becoming circular. Instead, they stretch and squeeze it, maintaining its eccentricity. This constant gravitational kneading generates immense tidal friction inside Io, heating its interior to the point of becoming the most volcanically active body in the entire solar system. Its surface a constantly remodeled landscape of fiery vents and lava flows. This is resonance in action, not just organizing paths, but pumping energy into a system and fundamentally altering its very nature. Now, scale that Jovian example up to a galactic level. The resonant orbital dance between two galaxies acts as an external engine, driving internal changes with relentless precision. The rhythmic gravitational kicks don't just affect the overall trajectories of the galaxies, they set up powerful resonances within each galaxy's disk. These internal resonances can amplify the formation of bars, drive the growth of the central bulge, and dramatically enhance the efficiency of those all-important tidal forces. The resonance ensures that the tidal stretching is applied at the same phase of the galaxy's rotation each time, allowing the effects to build far beyond what a single, non-resonant pass could ever accomplish. It's this syncopated rhythm that allows a force as weak as gravity to overcome the immense self-gravity of an entire galaxy, patiently and methodically pulling it apart. This is the final piece of the puzzle that explains the precision we see in systems like the mice. Their stunningly symmetrical tails and coordinated bursts of star formation are not the product of a single, violent event. They are the masterpiece of resonance, the culmination of countless gentle gravitational pushes, each one perfectly timed, each one building upon the last. The orbit is precise because it is resonant. It has found a natural frequency of the combined system and is exploiting it with the patience of the cosmos itself. It's this harnessing of the system's own natural rhythms that transforms a gentle influence into an irresistible force, a phenomenon that can orchestrate chaos into order and ultimately bring two mighty galaxies to their knees. For centuries, the story of interacting galaxies was written in theoretical equations and speculative sketches, a compelling narrative without its most crucial chapter, proof. That all changed when we turned our most powerful eyes to the sky, transforming abstract orbital mechanics into observable, measurable reality. The Hubble Space Telescope, floating above the distorting veil of Earth's atmosphere, provided the first crystal-clear portraits of these cosmic dances, capturing the delicate filaments of tidal tails and the distorted shapes of merging pairs with breathtaking detail. But Hubble's stunning visible light images were only part of the story. To truly understand the dynamics at play, we needed to see the motion, to measure the velocities, and to peer through the obscuring dust. This is where an entire suite of astronomical instruments, both in space and on high mountaintops, joined the chorus, each adding its unique voice to confirm the predictions of orbital theory. The real confirmation came not from a single picture, but from the meticulous analysis of starlight itself through spectroscopy. By dissecting the light from thousands of individual stars within a system like the mice, astronomers can use the Doppler effect to measure their line of sight velocity with incredible precision. Imagine charting the movement of every car in two merging traffic jams from hundreds of miles away. The data would seem chaotic, but when researchers did this for our galactic pair, a stunning pattern emerged. They found that stars on one side of a tidal tail were all systematically redshifted, hurtling away from us, while stars on the opposite side were blue-shifted, rushing toward us. This wasn't random motion, it was a coordinated flow, a clear and powerful signature of rotation. The entire stream was moving in a coherent, organized pattern, exactly as predicted by models of stars shepherded by tidal forces along a precise orbital path. This velocity map is the smoking gun, the direct observational evidence that the beautiful tails are not static sculptures but dynamic tracers of the galaxy's gravitational dance. Another crucial piece of evidence lies in the precise geometry of the encounter itself. Computer simulations consistently showed that for a tidal tail to form long and narrow, as we see in the mice, the interaction had to be almost perfectly prograde. This means the intruder galaxy's orbital path needed to align with the rotational plane of the disk it was perturbing. It's the difference between gently brushing your hand across the surface of a spinning pottery wheel, which throws clay out in a smooth ribbon, and punching it from above, which just makes a messy dent. When astronomers measured the orientation of the tidal tails relative to the disks of the parent galaxies, they found that stunning alignment. The tails erupt from the galaxies not at random angles, but directly along the plane of the orbital path, a beautiful confirmation that the geometry of the encounter is every bit as important as the force behind it. This alignment is a direct, observable signature of the orbital inclination, a key parameter that theorists had identified as critical for creating such spectacular and precise structures. The view across different wavelengths of light adds even more layers of confirmation. While Hubble shows us the starlight, the Chandra X-ray Observatory peers into the violent, high-energy aftermath of the encounter. It reveals vast clouds of multimillion-degree gas that have been shock-heated by the collision of interstellar media, or the brilliant glow of material accreting onto activated supermassive black holes processes that are direct consequences of the orbital dynamics funneling gas into the galactic cores. Meanwhile, radio telescopes like the Atacama Large Millimeter Array, or ALMA, pierce through the obscuring dust to map the cold molecular hydrogen that is the raw fuel for star formation. ALMA observations show how this gas isn't just scattered randomly. It is organized into intricate networks of filaments and dense knots, precisely tracing the flow patterns predicted by simulations of gas caught in a resonant gravitational tug of war. Each wavelength of light acts as a different instrument in the orchestra, all playing the same symphony of orbital motion. This revolutionary ability to compare theory directly with observation has been a watershed moment for cosmology. As renowned astronomer Dr. Sandra Faber once reflected, the progress in our field has been driven by new technology. It's that simple. Every time we build a bigger telescope or a new kind of detector, we discover something that shakes the foundations. Her words capture the essence of this journey. The development of digital light sensors, adaptive optics to correct for atmospheric blurring, and the launch of space observatories didn't just give us prettier pictures. They provided the quantitative data needed to test our ideas with rigor. We are no longer just imagining what might happen when galaxies meet. We are forensically reconstructing events that occurred 100 million years ago, using the frozen light and the coordinated motions of stars as our evidence. This transforms the entire endeavor from speculative philosophy into a hard science, where orbital models must answer to the court of observational data. This body of evidence does more than just validate a single theory. It reinforces the entire scientific method. We live in a universe governed by physical laws that are consistent across time and space. The same mathematics that describes the orbit of the Moon around the Earth can, when scaled up and fed into a supercomputer, predict the motion of billions of stars in a galactic encounter. The fact that the real universe, when we look at it with ever sharper eyes, matches these predictions so closely is a profound testament to the power of human curiosity and reason. It shows that through a combination of elegant theory, technological innovation, and painstaking observation, we can decode the mysteries of the cosmos, turning the silent, majestic dance of galaxies into a story we can finally begin to understand. But to fully grasp just how special and rare this kind of precision really is, we need to leave the elegant dance of the mice behind and step into a more chaotic cosmic arena. For every encounter that achieves this level of gravitational grace, there are countless others that play out like a demolition derby. The universe is filled with messy, violent, and spectacularly disruptive mergers, and perhaps the most famous example of this is a pair known as the antennae galaxies. Located about 60 million light-years away, these two spirals are named for the two vast, sweeping arcs of stars that extend outward, resembling the antennae of some gigantic insect. While they might look superficially similar to the tails of the mice, their origin story and their ultimate fate are worlds apart, born from a fundamentally different and far more chaotic kind of orbital interaction. The story of the antennae begins with a crucial mistake in their initial approach. Unlike the precise, prograde orbit that allowed the mice to brush past each other with a graceful, rhythmic tug, the two galaxies that would become the antennae are thought to have come together on a much more direct and disruptive path. Many simulations suggest their initial encounter was more head-on or at a much steeper, more perpendicular angle relative to their disks. This is the equivalent of a sideswipe rather than a gentle handshake. This kind of orbital geometry is brutally inefficient. Instead of applying tidal forces in a smooth, resonant rhythm that builds effects gradually, it delivers a single, massive gravitational shockwave that violently jolts both systems at once. The resulting tails aren't the product of patient shepherding. They are the splash from a high-speed impact, a chaotic splatter of stars and gas flung out in a messy, disorganized spray. The aftermath of this chaotic encounter is a scene of utter pandemonium compared to the ordered transformation of the mice. Within the antennae, the clear, distinct structures of the original spiral disks have been almost completely obliterated. There is no sense of two separate entities engaged in a dance. Instead, we see a turbulent, boiling cauldron of stellar material. The gravitational shockwaves have triggered starbursts so intense and so widespread that they are tearing the galaxies apart from the inside out. The formation of new, massive stars is happening at such a ferocious rate that their subsequent supernova explosions are creating a continuous feedback loop of violence, heating and expelling gas that might have otherwise formed future generations of stars. It's a firestorm of creation that borders on self-destruction, a far cry from the more regulated bursts we see in the mice. The outcome here isn't a prolonged, precise interaction. It's a rapid, messy, and irreversible collision course. These two galaxies are not going to fly apart. They are destined to merge into a single, new entity in a comparatively short cosmic time frame, their individual identities forever erased in the chaos. This stark contrast highlights a profound truth about galactic evolution. The initial orbital parameters are everything. They are the first domino in a chain of events that dictates the entire future of the interaction. A near miss with a precise, prograde orbit creates a system like the mice, a long-lived laboratory of tidal forces and resonant effects. A direct hit or a highly inclined orbit creates a system like the antennae, a short-lived, violent burst of activity that quickly culminates in a merger. It's the difference between a master chef gently folding ingredients together to create a delicate soufflé and simply throwing them all into a blender. Both processes combine the materials, but the results and the subtlety of the final product could not be more different. The orbit is the recipe, and the universe is a kitchen where only a select few combinations yield a result of such refined precision. This rarity is a key point emphasized by experts who study these interactions. While galactic encounters are common throughout the universe, especially in the crowded environments of galaxy clusters, the specific conditions required for a truly precise, resonant, and long-lived dance are exceptionally uncommon. It requires a very specific combination of mass, velocity, and approach angle, a celestial Goldilocks zone where everything is just right. This makes systems like the mice incredibly valuable to astronomers. They are not just beautiful curiosities, they are pristine laboratories. Their stability and predictability allow scientists to test the laws of gravity and the properties of dark matter with a level of detail that is impossible in the chaotic wreckage of a merger. In the messy antennae, it's difficult to disentangle one effect from another. Everything is happening at once. But in the mice, the clean, ordered progression of the encounter allows researchers to isolate specific processes, to watch how a tidal tail grows over time, or to measure exactly how gas is compressed to trigger star formation. They are the controlled experiments in a field of science that usually only offers us natural disasters to observe. Reflecting on this cosmic spectrum from order to chaos does more than just satisfy our scientific curiosity. It reshapes our perception of the universe itself. We often think of space as a place of either serene emptiness or violent explosions, but the reality is far more nuanced. The universe operates on a razor's edge, a fine line where the slightest variation in initial conditions, a fraction of a degree in angle, a minuscule percentage of velocity, can determine whether a galactic encounter becomes a creative, transformative dance or a destructive, consumptive crash. This isn't just about galaxies. It's a fundamental principle of a cosmos governed by physical law. It reveals a universe where precision is not an abstract concept, but a powerful, tangible force that can dictate the fate of hundreds of billions of stars, steering them away from chaos and toward a more ordered and ultimately more illuminating destiny. So where does this magnificent dance ultimately lead? After the final gravitational embrace, after the last stars are flung into tidal streams and the last waves of star formation have blazed and faded, what remains of these two mighty galaxies? The answer lies billions of years in the future, a destiny written in the language of their initial orbital energy. Despite the seeming permanence of their current entangled state, their long-term fate hinges on a simple cosmic equation. Did their encounter leave them with enough combined kinetic energy to overcome their mutual gravitational attraction, or were they forever bound by that first fateful touch? In the first scenario, the galaxies experienced what astronomers term a flyby. Their precise orbit, while transformative, was just fast and wide enough. They swung past each other in a grand arc, close enough to tear each other apart gravitationally, but still carrying too much momentum to be captured. After their closest approach, they continue on, forever altered, sailing apart on new trajectories into the intergalactic void. They do not merge. Instead, they become two separate but deeply wounded galaxies. Their beautiful spiral structures are likely gone forever, replaced by a more irregular, puffed-up morphology. They will carry the spectacular scars of their encounter for the rest of their existence. Those long, graceful tails of exiled stars will slowly fade but never fully disappear, becoming permanent monuments to their brief cosmic affair. Their interstellar gas, much of it consumed in the starbursts or blown away by supernova winds, will be depleted, leaving them gas-poor and unable to form many new stars in the future. They will age, their stellar populations growing older and redder, two lonely islands forever bearing the marks of a passionate but fleeting gravitational dance. The second, and for a precise orbit more likely outcome, is the complete and total merger. This is the final act, the consummation of the gravitational bond formed all those millions of years ago. If their orbital energy was insufficient to escape, the galaxies do not fly apart after their first pass. They reach the apex of their swing and then, pulled by the relentless hand of gravity, they fall back toward each other. This begins a decaying orbital dance, a series of ever closer passes. With each subsequent loop, they transfer more energy and angular momentum to their outer stars and to the dark matter halo, which acts as a gravitational reservoir. This energy loss causes their orbits to tighten, drawing them closer together in a fatal spiral. The final merger is not a single, explosive event, but a slow, grinding process that can take hundreds of millions of years. The individual identities of the two spirals are completely erased, their stars violently mixed into a single, new entity. The elegant disk structures are destroyed, replaced by a random, swarm-like distribution of stars. The end product of this colossal unification is almost always a giant elliptical galaxy, a featureless, football-shaped collection of old, red stars, a quiet and sedate retirement home for the stellar populations of two once vibrant spirals. The silent architect ensuring this final binding is once again the dark matter halo. Its immense gravitational pull is the glue that holds the entire encounter together. As the visible galaxies interact, their dark matter halos are the first to merge, creating a deep, common gravitational well that the visible matter cannot escape. The role of dark matter is to provide the extra mass, the additional gravitational grip that captures the galaxies and ensures they cannot fly apart. As Dr. T.J. Cox, who led influential simulations of galaxy mergers, has elucidated, the dark matter halo is the ultimate arbiter of a merger's fate. It dictates the dynamical friction that saps the orbital energy, slowly dragging the galaxies together. Without these massive halos, galaxies would simply bounce off each other like rubber balls. His work on modeling merger remnants shows how the properties of the final elliptical, its size, its shape, its velocity dispersion, are direct descendants of the initial masses and orbits of the progenitor spirals and their dark matter components. Pondering these distant futures on scales of billions of years is a profoundly humbling exercise. It forces us to confront the sheer patience of the cosmos, where a single event, set in motion by the precise alignment of two paths, unfolds with an inevitability that dwarfs all of human history. The outcome of this dance will reshape the local universe, creating a new gravitational center that will influence smaller galaxies for eons to come. It illustrates a powerful truth. In the grand architecture of the cosmos, nothing is truly isolated. A single, precise orbit, a fleeting gravitational handshake across the void, can set in motion a chain of events that culminates in the birth of a galactic giant, its legacy echoing through eternity long after the last notes of the dance have faded into silence. To truly decode the silent, slow-motion ballet of galaxies, we need more than just mathematical predictions. We need to witness it, and that requires turning our entire planet into a listening post, equipping it with technological marvels that can capture the faint whispers of the cosmos across the entire spectrum of light. This isn't about a single telescope, it's about a coordinated orchestra of instruments, each playing a different part to reveal the full symphony of an orbital encounter. From the cold, thin air of the Chilean high desert to the silent, sun-drenched void a million miles from Earth, our tools are the extensions of our senses, built to perceive the forces and flows that sculpt the universe. For mapping the raw fuel of this galactic dance, the cold, dark clouds of molecular gas nothing is more powerful than a radio telescope, and the undisputed champion is the Atacama Large Millimeter Array, or ALMA. Perched at an altitude of over 16,000 feet in the Chilean Andes, ALMA is not a single dish but a symphony of 66 high-precision antennas that can be moved across the desert floor to act as one gigantic eye on the sky. Its specialty is tuning into the faint radio waves emitted by molecules like carbon monoxide, which serves as a tracer for the otherwise invisible hydrogen gas that fills interstellar space. When trained on a system like the mice, ALMA doesn't see the brilliant stars. It reveals the intricate skeleton of gas flows beneath. It shows us the vast rivers of cold hydrogen being funneled by the tidal forces, the dense knots where that gas is collapsing to form new stars, and the delicate filaments that trace the precise gravitational pathways of the orbit itself. It is the ultimate cartographer of the cosmic fuel supply, showing us how the orbital mechanics direct the very stuff of creation. But to understand the motion, to measure the speeds and directions that prove the orbital models, we need the power of spectroscopy. This is the art of dissecting starlight into its constituent colors, its spectrum, and reading it like a cosmic barcode. Every element in a star's atmosphere absorbs specific wavelengths of light, creating unique dark lines in that spectrum. The Doppler effect then takes over. If a star is moving toward us, those lines are shifted toward the blue end of the spectrum. If it's moving away, they shift to the red. By using incredibly sensitive spectrographs attached to the world's largest telescope's instruments like the Keck Observatory's high-resolution spectrometers, astronomers can measure this shift for thousands of individual stars within a galactic encounter. They can create a detailed velocity map showing which stars are rushing toward us and which are flying away. This is how we transform a beautiful picture into a dynamic dataset. The coordinated flow of stars within a tidal tail, all moving in the same direction at the same speed, is the incontrovertible proof that we are seeing a structured orbital flow, not a random explosion. To pierce through the veils of obscuring dust that hide the most intense action, we must leave Earth's atmosphere behind. Dust clouds that are opaque to visible light are often transparent to longer wavelength infrared radiation. This is the domain of the James Webb Space Telescope, a technological masterpiece that operates at a gravitationally stable point beyond the Moon. JWST exquisite infrared vision is revolutionizing our view of galactic interactions. It can stare directly into the heart of the violent starburst regions triggered by the orbital encounter, seeing the brilliant glow of newborn stars still embedded in their dusty cocoons. It can detect the faint heat signature of the oldest, coolest stars, allowing us to trace the full extent of the tidal distortions. As Dr. Marcia Reek, a pivotal leader for one of Webb's key instruments, has explained, infrared astronomy is like getting a master key to the universe. It unlocks doors that have been closed to us, allowing us to see the processes of star and planet formation that are hidden behind dust. Webb doesn't just show us the aftermath, it shows us the ongoing creation in stunning, unprecedented detail. This synergy between different tools is what turns speculation into certainty. The Hubble Space Telescope provides the sharp, visible light portraits that reveal the dramatic structure of the tidal tails. The Chandra X-ray Observatory detects the multimillion-degree gas heated by supernova explosions within those starbursts, painting a picture of the violent feedback that regulates star formation. And ground-based telescopes with adaptive optics systems technology that uses laser guide stars to correct for the blurring of Earth's atmosphere in real time, provide the high-resolution spectroscopic data to measure stellar motions with pinpoint accuracy. Each observatory, each instrument contributes a single piece of the puzzle: a radio map from ALMA, a velocity measurement from Keck, an infrared image from Webb. Individually, they are fascinating. Combined, they form an irrefutable and multi-dimensional movie of a gravitational encounter, confirming the predictions of orbital mechanics with a wealth of evidence that would have been unimaginable just a generation ago. This collaborative effort across technologies and wavelengths is the greatest testament to human curiosity, a global endeavor to build the machines that can finally let us see the music of the spheres. Yet for all the breathtaking progress we've made in mapping the gravitational dance of galaxies, in running sophisticated simulations that can predict the formation of tidal tails and starbursts, the universe remains a place of profound and humbling mystery. Our understanding of orbital dynamics, as precise as it seems, is built upon a foundation that is still full of cracks and unanswered questions. Each new discovery from our telescopes and supercomputers doesn't just provide answers. It often peels back a layer to reveal an even deeper, more complex puzzle waiting beneath, reminding us that for every law of physics we've decoded, there are a dozen phenomena that still defy our current models. One of the most glaring gaps in our knowledge revolves around the very architect of these precise orbits, dark matter itself. We can map its distribution through its gravitational effects. We know it constitutes the vast majority of the matter in the universe, but we still have no idea what it actually is. This ignorance has direct, frustrating consequences for our orbital models. Our simulations rely on certain assumptions about how dark matter behaves, typically that it is cold and collisionless, meaning the particles don't interact with each other or with light, only through gravity. But what if that's not entirely true? Some theorists propose alternative models where dark matter has some slight interaction force, or is fuzzy, or even exists in a complex hidden sector with its own rich physics. Each of these possibilities would fundamentally alter how dark matter halos form and evolve. A slightly warm dark matter particle, for instance, would suppress the formation of very small-scale structures within the halo, which could change the gravitational granularity that stars and gas clouds feel as they orbit. These subtle differences could be the key to explaining why some encounters produce such clean, precise tidal features while others, with seemingly similar initial conditions, descend into chaos. Until we can directly detect and characterize a dark matter particle here on Earth, our most sophisticated galactic models are built on a best guess, a shadowy approximation of the true cosmic scaffolding. This leads directly to another vexing puzzle, the core cusp problem. Our simulations of dark matter halos consistently predict that they should have a cusp, a very steeply rising density gradient toward the center of a galaxy. However, observations of the motions of stars and gas in the inner regions of many dwarf and low surface brightness galaxies suggest something quite different, that many dark matter halos have a constant density core. This isn't just a minor discrepancy, it's a direct challenge to the standard model of cosmology. If our understanding of how dark matter clumps under gravity is wrong on the scale of individual galaxies, then everything we think we know about how those galaxies interact and merge is thrown into question. The precise orbital decays we simulate, the transfer of angular momentum, the very timescales for mergers, all of it could be off. Resolving this tension is one of the most active and contentious areas of astrophysics today, with some scientists proposing new dark matter physics and others searching for astrophysical solutions involving powerful supernova winds that might have blown the dark matter out from the centers. The answer will rewrite the rules of the gravitational dance. Beyond the mysteries of dark matter lie equally profound questions about the initial conditions themselves. Why do some interactions, like the one between the mice, result in such a spectacularly precise and resonant orbit, while others, like the antennae galaxies, are messy and disruptive from the start? Is it simply a cosmic lottery, a random distribution of approach angles and velocities, or are there deeper, hidden factors at play that we haven't yet learned to measure? Perhaps the history of a galaxy long before it meets its partner holds the key, a galaxy that has already cannibalized several small dwarf galaxies may have a more perturbed, heated disk of stars, making it more susceptible to disruption. Another galaxy might have a very different gas fraction. A gas-rich galaxy is more pliable, its material able to flow and respond to tidal forces more easily, potentially leading to more dramatic and ordered structures than a gas-poor, red and dead elliptical. The work of pioneering dynamicists like Dr. Scott Tremaine has long focused on these statistical questions, trying to understand the chaotic dynamics of multi-body systems and why certain stable configurations emerge from the randomness. As he has often noted, the universe is under no obligation to make things simple for us. The sheer number of variables involved makes it incredibly difficult to isolate a single reason for the beautiful precision we see in some encounters. These are not merely academic curiosities, they are the bleeding edge of human knowledge, the frontier where our current models break down and where the next great leap in understanding must occur. This constant state of questioning is not a weakness of science, it is its greatest strength. It is the engine of progress. Every unsolved mystery is a beacon, guiding the next generation of telescopes, space missions, and theoretical breakthroughs. The upcoming Vera C. Rubin Observatory will catalog billions of galaxies, providing a vast statistical sample of interacting pairs that will finally allow us to move beyond studying individual beautiful examples to understanding the full population. The European Space Agency's LISA mission will open a new window on the universe by detecting gravitational waves from merging supermassive black holes, directly probing the final moments of the orbital decay that our optical telescopes can only infer. These tools will provide the data needed to test our wildest ideas and to challenge our most cherished assumptions. Embracing these unknowns is what transforms astronomy from a mere cataloging of the heavens into a truly human endeavor. It connects us to the first stargazers who looked up and wondered, to the classical astronomers who plotted the paths of planets with nothing but naked eye and patience, and to the modern scientists who code equations that unfold over millions of years in a supercomputer's memory. The cosmos does not give up its secrets easily. Each answer is hard-won, and each new discovery reveals a horizon even more vast and mysterious than the last. This endless frontier of questions is not a barrier to our understanding, but the very thing that makes the exploration so exhilarating, a perpetual reminder that the universe will always have deeper layers of wonder waiting for those curious enough to look. This galactic ballet, this precise orbital dance between two colossal islands of stars, is far more than just a spectacular light show in the distant void. It is a fundamental experiment, a cosmic laboratory that reveals the deepest operating principles of the entire universe. By meticulously studying the clockwork mechanics of this single, intricate encounter, we are handed a key that unlocks truths about the nature of reality on the grandest possible scales. The elegant predictability of these motions, governed by the relentless pull of gravity, is a powerful testament to a universe that is not chaotic and random, but one that is ordered, mathematical, and ultimately knowable. It proves that the same physical laws we've deduced from watching an apple fall or a planet orbit our sun hold sway over the motions of hundreds of billions of stars separated by millions of light years. This isn't just a local ordinance of physics, it is a universal constitution, and these interacting galaxies are showing us that it applies everywhere, always. Perhaps the most profound implication is the overwhelming evidence it provides for the dominance of dark matter. We cannot see it, we cannot touch it, but we can watch its invisible hand guide the entire performance. The precise geometry of the tidal tails, the specific orbital velocities of the stars within them, and the very fact that the galaxies are held together in this dance at all of this points to a gravitational force that is far stronger than the visible stars and gas can account for. This one local encounter becomes a microcosm for the entire cosmos, screaming at us that the universe we see is just the visible tip of a much larger, darker iceberg. It forces us to accept that the vast majority of the universe's material content is made of something entirely alien to our everyday experience, a shadowy component that dictates the architecture of everything. This isn't a minor detail, it is a fundamental rewriting of the cosmic inventory, and it all comes from carefully observing how things move. These local dynamics also act as a crucial time machine, allowing us to peer back into the history of cosmic structure formation itself. The prevailing model of our universe, the lambda-cold dark matter model, posits that the large-scale structure we see today, the vast cosmic web of filaments and clusters, grew from tiny quantum fluctuations in the primordial fireball of the Big Bang. But how did those infinitesimal ripples evolve into the magnificent galaxies we see today? The answer is through a hierarchical process of mergers and acquisitions, a cosmic history of gravitational gathering. A precise encounter like the one between the mice is not a rare oddity. It is a standard chapter in the life story of almost every galaxy we see. Our own Milky Way bears the scars of past mergers in the form of stellar streams and its surrounding halo of old stars. By studying this process in action elsewhere, we are watching the primary mechanism of galactic growth and evolution unfold before our eyes. We are witnessing how small structures built themselves into the giants that now dot the cosmos. This understanding inevitably pulls our gaze toward the ultimate fate of everything. The same gravitational force that orchestrates these beautiful local dances is also the master of the universe's long-term destiny. The precise exchange of energy and angular momentum we see in a galactic encounter is a local example of the gravitational processes that govern the expansion of the universe itself. Will the gravitational pull of all matter, both light and dark, eventually halt and reverse the expansion, leading to a big crunch? Or will the mysterious force of dark energy continue to accelerate the expansion, eventually pulling all galaxies apart in a big freeze, leaving them isolated and starved of new interactions? While the fate of the entire cosmos is dictated by the balance between dark matter and dark energy, the fundamental rules of that engagement, the gravitational interactions, the transfer of energy are being worked out in miniature right here in the orbital decay of two merging galaxies. As the renowned cosmologist Dr. Martin Rees has often articulated, the cosmos is all there is or ever was or ever will be. To understand the grand narrative, we must learn to read the local stanzas. A single galactic encounter is one such stanza, a verse that rhymes with the entire epic poem of the universe. Furthermore, this local precision forces us to confront the staggering scale of cosmic time. The fact that we can predict the motions of galaxies over hundreds of millions of years speaks to the incredible stability of the physical laws we've discovered. It reveals a universe that operates with a patience that is almost incomprehensible to our fleeting human lifespans. The outcomes we model in our simulations, the final merger into an elliptical galaxy, for instance, will not occur for billions of years. This stretches our perspective, connecting the fiery beginnings of the universe in the Big Bang to its distant, cold future. It shows us that we are living in a special, dynamic era, the stelliferous era, dominated by shining stars and interacting galaxies, a vibrant middle chapter in a story that spans from an unimaginable beginning to an uncertain, distant end. By understanding the local mechanics, we gain a humbling appreciation for our place not just in space, but in the deep, flowing river of cosmic time, a fleeting moment in which we are privileged to observe and comprehend the majestic, slow-motion ballet that is the evolution of the universe itself. Wrapping our minds around the sheer scale of these events is perhaps the greatest challenge of all. We can speak of hundreds of millions of years and hundreds of thousands of light years, but these numbers are so vast they become almost meaningless abstractions, empty labels for distances and durations that our brains simply aren't wired to comprehend. To truly feel the weight of this galactic dance, we need to bring it down to a human scale, to find an analogy that bridges the chasm between our everyday experience and the cosmos. Imagine for a moment that our entire Milky Way galaxy is not a sprawling pinwheel of hundreds of billions of stars, but something far more familiar, a great glowing metropolis like New York City. In this scaled-down model, our sun is nothing more than a single grain of sand on a sidewalk in Brooklyn, and the Earth is a microscopic speck orbiting that grain. The vast, empty spaces between stars become the city blocks and parks, and the journey of light from one side of the galaxy to the other is a trip that would take you from the Bronx to the southern tip of Staten Island. Now bring in the second galaxy, our cosmic dance partner. In this model, it's another immense city, perhaps the size of Chicago, traveling through the void on a path that will bring it breathtakingly close to our own galactic metropolis. The distance of closest approach, the point where their gravitational embrace is most intense, might be equivalent to just a few city blocks, but here is where the analogy reveals the truly stunning precision of the event. These two entire cities, each containing the equivalent of every building, every person, every car, and every streetlight, are not just passing at a safe distance. They are moving relative to each other at a stately, almost pedestrian pace, a walking speed of just a few miles per hour. And yet, despite their immense size and this relatively slow speed, their trajectories are so perfectly aligned that they pass within mere inches of each other. Not a single building touches, not a single streetlight is clipped, but the gravitational wake of their passing, the subtle pull of every single component, is enough to send tremors through both cities, pulling streams of dust and debris out into long, graceful arcs between them and triggering frantic bursts of construction and activity in their cores. This is the level of precision we are talking about, a clean, graceful, impossibly close pass executed on a scale so grand it defies belief, all governed by the same silent, predictable laws of physics. This act of scaling down is not just a fun, intellectual exercise. It is a vital tool for connection. It was a technique championed and perfected by the late, great astronomer Carl Sagan, who who understood that science wasn't just about data and equations, but about story and wonder. He famously described our planet as a pale blue dot, a single pixel in a vast cosmic portrait, a perspective designed not to diminish us, but to instill a profound sense of awe and a humbling recognition of our true place in the universe. By translating the impossibly large into the intimately relatable, we do more than just understand the numbers, we feel them, we internalize the grandeur. The abstract concept of a galactic orbit ceases to be a dry mathematical formula and becomes a story of two immense, sentient-seeming entities engaged in a slow, graceful, and powerful dance. It transforms the cosmos from a cold, indifferent void into a place of majestic, clockwork beauty, a place where events of breathtaking precision unfold all around us, unseen only because we lack the timescale to perceive them. This shift in perspective is deeply humbling, but it is also incredibly empowering. It demonstrates a powerful, unifying truth about our universe. The same fundamental laws of physics that govern the motion of a galaxy containing hundreds of billions of stars also dictate the path of a baseball arcing through the air on a summer afternoon. The gravity that holds you in your chair is the very same force that shepherds stars into tidal streams and holds entire clusters of galaxies together. There is no separate set of rules for the cosmos and a different one for Earth. There is one physics, one set of equations, one universal constitution that applies equally to the quark and the quasar. This realization connects us to the cosmos in the most fundamental way possible. The iron in your blood was forged in the heart of a massive star that died in a spectacular supernova explosion billions of years ago. The calcium in your bones was likely part of that same stellar debris, eventually finding its way into the dusty cloud that collapsed to form our sun and its planets. You are not just a passive observer of the universe, you are a product of it, a collection of atoms that has been part of this grand cosmic cycle for nearly 14 billion years, now temporarily arranged in a form complex enough to look back out at the universe and wonder about its origins. This personal touch is the final, crucial step in making these colossal concepts not just understandable, but meaningful. It moves the narrative from something that happens out there to something that is intimately connected to right here. It allows a viewer to internalize the grandeur, to take the immense, silent movie of galactic collision and find their own place within its narrative. The precise orbit that brought two galaxies to their knees is no longer just a distant astrophysical phenomenon. It becomes a testament to the elegant order that underpins all of reality, an order that we are a part of. It transforms the audience from passive recipients of information into active participants in a cosmic story, fostering a sense of wonder that is the true heart of scientific discovery and the most powerful reminder that our thirst to explore the universe is, in the end, the universe beginning to explore itself. But this journey of cosmic discovery, this ever-deepening understanding of the precise forces that shape reality, comes with a profound and often unspoken responsibility. For centuries, our relationship with the universe has been one of passive observation, of simply trying to comprehend the rules of a game we had no hope of influencing. But that era is ending. The same knowledge that allows us to predict the orbital dance of galaxies with such stunning accuracy is also the foundational knowledge that could one day grant us the power to alter such events. We are moving from being mere spectators of the cosmos to potential participants, and this transition forces upon us a series of ethical dilemmas as vast and complex as the universe itself. The question is no longer just can we understand these forces, but should we ever seek to wield them, and if so, with what wisdom and for what purpose? Consider the long-term trajectory of our species. Our mastery of orbital mechanics has already allowed us to place satellites for communication, to send probes to every planet in our solar system, and to build a permanent outpost in low Earth orbit with the International Space Station. This is the most basic application of this knowledge, using a precise understanding of gravity to navigate our local neighborhood. But the logical extension of this path is staggering. If we can harness the gravity of planets for slingshot maneuvers to reach the outer solar system, could we one day learn to manipulate gravitational fields themselves? Concepts that sound like pure science fiction today, like constructing a Dyson sphere to harness a star's entire energy output, or nudging a near-Earth asteroid onto a new course, not just to avoid an impact, but to direct it toward a mining operation, are, in theory, applications of the very physics we are discussing. This knowledge grants us a form of cosmic agency, and with agency comes an immense ethical burden. The philosopher Dr. Nick Bostrom, who directs the Future of Humanity Institute, often frames this in terms of existential risk and stewardship. He argues that as our power grows, so does our potential to make catastrophic mistakes on a planetary or even stellar scale. A miscalculation in a large-scale engineering project could inadvertently destabilize a delicate orbital balance, with consequences echoing for millennia. Our responsibility, therefore, is to couple our growing technological prowess with an equally mature ethical framework, one that prioritizes the long-term survival and flourishing of intelligent life, both here and potentially elsewhere. This leads to the most speculative yet most profound ethical question. If we one day confirm that a neighboring star system is on a collision course with another, or that a habitable world is doomed to be ripped apart by tidal forces in 1 billion years, do we have any moral obligation to intervene? Is our role simply to observe and document the cosmos in all its violent beauty, or does the unique gift of our consciousness and our knowledge come with a duty to act as caretakers, to prevent what we might see as cosmic tragedies? This isn't about our current capabilities. It's about setting a philosophical precedent for the future. Intervention on such a scale would be the ultimate expression of our understanding of precise orbits, but it would also be an arrogant assumption that we know what's best for the universe. The natural processes of galactic collision and stellar death are what create the heavy elements necessary for planets and life. To stop one might be to prevent the rise of future civilizations elsewhere. This is the ultimate ethical tightrope, balancing a compassionate desire to preserve with a humble acknowledgement that destruction and creation are two sides of the same cosmic coin. Beyond these grand hypotheticals, this knowledge fundamentally reshapes our world, here on Earth. Understanding that our planet, our solar system, and even our galaxy are not immutable, permanent fixtures, but are transient players in a dynamic and often violent cosmic ballet can be deeply unsettling. It instills a sense of planetary fragility. A nearby supernova, a gamma-ray burst, or even a subtle change in the dark matter density of our region could have catastrophic consequences for life on Earth. This perspective can foster a new kind of global consciousness, a recognition that all of humanity shares a common, tiny lifeboat adrift in a vast and unpredictable ocean. The political and cultural divisions that seem so all-consuming from our surface perspective shrink into insignificance against the backdrop of galactic time and astronomical forces. This cosmic humility could be the most valuable ethical takeaway, fostering a spirit of international cooperation and long-term thinking that is desperately needed to address the challenges we face on our own world. Ultimately, the study of precise orbits and galactic dynamics is far more than a scientific pursuit. It is a formative step in the maturation of a species. It is the process of growing up, of looking up from our cradle and finally beginning to understand the true nature of our home and the neighborhood it resides in. This knowledge doesn't just fill textbooks, it shapes our identity. It challenges us to define what kind of cosmic citizens we want to be. Do we want to be the species that learned the rules of the universe only to use them for short-sighted gain? Or do we want to be the species that used its knowledge to carefully steward its own world while respectfully exploring the greater cosmos with a blend of awe, curiosity, and profound responsibility? The answers to these questions won't be found in a telescope or a supercomputer, but in the human heart. The equations of orbital mechanics tell us what is possible, but only our ethics, our empathy, and our wisdom can guide us toward what is right, ensuring that our first tentative steps into a wider universe are taken not as conquerors, but as thoughtful, humble guests. The beauty of these cosmic encounters isn't reserved for those with advanced degrees in astrophysics. It's a story meant for everyone, and sharing it requires translating the immensely complex into the powerfully simple. This is where the art of education transforms from mere explanation into genuine inspiration, using clever tools and relatable metaphors to build a bridge over the vast moat of technical jargon. Imagine trying to explain the warping of spacetime to a curious 10-year-old. You could dive into the tensor calculus of general relativity, or you could take a large, stretchy rubber sheet, suspend it tightly, and place a heavy bowling ball in the center. The way the ball creates a deep depression, causing smaller marbles to roll around it in elliptical paths, isn't just a cute demo. It's a direct, visceral analog for how mass tells spacetime how to curve, and how that curvature tells objects how to move. Suddenly, a concept that baffled the greatest minds for centuries becomes an intuitive, tangible experience. This kind of hands-on modeling is a master key that unlocks abstract principles, making the invisible forces that govern galaxies feel as real as gravity itself. In our digital age, this outreach extends far beyond the classroom rubber sheet. We now have the extraordinary power to put the fate of entire galaxies into the hands of anyone with a smartphone or a computer. Interactive simulations and mobile apps have become the planetariums of the 21st century, dynamic tools that allow users to become cosmic choreographers. Applications like Universe Sandbox let you experiment with the very physics we've been exploring. You can recreate the encounter between the mice, tweaking the initial velocity or the angle of approach with a finger swipe, and watch in real time as your changes either create beautiful tidal tails or lead to a messy, immediate merger. This transforms a passive viewer into an active participant. There's a profound difference between being told that orbital resonance is important and being able to adjust the orbital periods of two digital galaxies until you see their gravitational nudges suddenly sync up, amplifying their effects right before your eyes. This trial-and-error exploration fosters a much deeper, more intuitive understanding than any textbook diagram ever could, because the user is not memorizing a fact. They are discovering a law of nature for themselves. At the heart of all these methods, from the simplest physical model to the most sophisticated simulation, lies the ancient and universal power of storytelling. Data points and equations are the skeleton of science, but narrative is the flesh and blood that gives it life and meaning. We don't just present a timeline of a galactic merger, we frame it as an epic drama with protagonists, conflict, and transformation. The two galaxies aren't anonymous blobs of stars, they are characters with histories and destinies. Their initial approach is the meeting of strangers, their close passage the climactic battle or dance, and their final fate, whether fly-by or merger, the resolution of their story. Experts like Dr. Neil deGrasse Tyson have built entire careers on this principle of demystification, passionately arguing that the universe's greatest stories are true ones. He often says that the job of a scientist and educator is to be a translator, to take the poetry of the cosmos and render it in a language that stirs the soul. By weaving facts into a compelling narrative, we stop teaching and start captivating. We're no longer just conveying information, we're sharing awe, and that emotional connection is what turns a casual interest into a lifelong passion. This mission of empowerment through education is perhaps the most crucial legacy of our cosmic curiosity. By equipping educators, parents, and community leaders with these strategies, interactive models, digital simulations, and powerful storytelling, we aren't just creating a handful of future astronomers. We are fostering a more scientifically literate and engaged public, a generation of thinkers who are comfortable with scale, comfortable with complexity, and humbled by their place in a vast and wondrous universe. This widespread understanding builds a societal resilience against misinformation and a deeper appreciation for the painstaking work of basic research. It ensures that the marvels revealed by our most powerful telescopes don't remain locked away in academic papers, but instead spark conversations around dinner tables and inspire wonder in young minds gazing up at a starry night sky. The precise orbit that brought two galaxies to their knees is a testament to the ordered beauty of physical law, and by sharing that story effectively, we ensure that its lessons in patience, precision, and interconnectedness resonate not just across space, but across generations. Translating the cold, precise mathematics of orbital dynamics into something the human heart can feel is a monumental task, one that requires a unique fusion of rigorous science and profound artistry. This is where the digital artist steps onto the stage, not as a mere illustrator of scientific facts, but as a vital translator and a co-explorer of cosmic truth. Armed with the same data sets used by astrophysicists, the velocity maps, the density plots, the gravitational calculations, these modern-day Da Vincis use their mastery of light, color, texture, and motion to breathe life into numbers. Their canvas is the supercomputer, their brush is sophisticated rendering software, and their mission is to make the invisible not just visible, but visceral. They take a billion data points plotting the trajectory of dark matter and transform it into a majestic, swirling halo of subtle light. They turn the abstract concept of a tidal force into a breathtaking, slow-motion visualization of a galaxy's stars being gently pulled into a luminous river of light. This process is far more than just making pretty pictures. It is a critical act of interpretation, a bridge of empathy built between the analytical mind and the awe-inspired soul. Some of the most iconic and trusted examples of this fusion come from the space agencies themselves. The Hubble Heritage Project stands as a legendary testament to this philosophy. While the raw data from the Hubble Space Telescope is a treasure trove of scientific information, it often arrives as grayscale images captured through specific filters that isolate the light of different elements. The Heritage team, comprising both astronomers and imaging specialists, makes a series of deliberate artistic choices. They assign vibrant colors to these filters, perhaps mapping hydrogen to red, oxygen to blue, and sulfur to green, not to falsify but to elucidate. This colorization highlights chemical composition, structural detail, and the immense physical scale in a way the human eye can immediately appreciate. The final result, like the famous image of the mice galaxies, is a masterpiece that is both scientifically accurate and artistically stunning. It reveals the delicate tapestry of dust lanes, the brilliant blue clusters of newborn stars, and the faint, ethereal glow of the tidal tails with a clarity and emotional impact that a graph of luminosity values could never achieve. These images become the public face of discovery, transforming distant astrophysical phenomena into cultural touchstones that adorn posters, desktop wallpapers, and the imaginations of millions. For the ultimate immersive experience, we turn to the digital domes of planetariums and IMAX theaters. Here, the collaboration between scientist and artist reaches its most spectacular form. Teams at institutions like NASA, a scientific visualization studio, and the American Museum of Natural History create full-dome films that are nothing short of cinematic magic. They take the N-body simulation data from supercomputers, the very same code that predicts the galaxy's motions, and use it to drive high-resolution, three-dimensional animations. This allows them to create a virtual camera and place it anywhere in the scene. You don't just watch the galaxies interact from a distant, static viewpoint. You soar alongside the tidal tails as they form. You dive into the glowing core of a starburst, and you witness the supermassive black holes at the centers of the galaxies begin their own gravitational dance. The artistic choices are paramount: the pacing of the fly-through, the subtle lighting that gives depth to the dark matter halos, the sound design that underscores the silent majesty of the event. This is science communication as an emotional and sensory experience, designed to make the viewer feel the immense scale and profound beauty of the event in their bones. Pioneering this very field of scientific visualization is Dr. Donna Cox, director of the Advanced Visualization Lab at the University of Illinois, and a true Renaissance figure who bridges the worlds of art and supercomputing. Her work and that of her team is foundational to how we all visualize complex scientific data. She famously described her team's process as that of Renaissance teams, where artists, computer scientists, and domain scientists work side by side from the very beginning of a project. In her view, the artist is not a service provider brought in at the end to make a graph look nice. They are an integral part of the discovery process itself. She has stated, visualization is a catalyst for discovery. The artist's eye can perceive patterns, anomalies, and relationships in the data that might otherwise be missed by automated analysis. This is a powerful concept that the aesthetic intuition of an artist can directly contribute to scientific insight. By crafting a visualization that feels dynamic and coherent, the artist might intuitively highlight a flow of gas or a resonance effect that leads the astrophysicist to ask a new question or re-examine an assumption. In this partnership, beauty becomes a tool for truth, and the artistic rendering becomes a hypothesis about how the universe might actually look and feel. This beautiful synergy between the analytical and the creative does more than just communicate facts. It fundamentally enriches our appreciation of the universe. A dry scientific paper detailing the orbital parameters of a galactic encounter can tell us the what and the how, but a masterfully crafted visualization of that same event, where two spiral galaxies dance in a silent, stately ballet set to an evocative score, tells us the why. It answers why we should care. It taps into a universal sense of wonder, transforming the abstract concept of orbital precision from a mathematical curiosity into a source of genuine inspiration and profound awe. It reminds us that the pursuit of knowledge is not a sterile, emotionless endeavor, but a deeply human one, driven by the same craving for beauty and understanding that has inspired artists for millennia. In the end, these artistic interpretations are a vital part of the scientific narrative, proving that to truly comprehend the cosmos, we need both the unerring logic of the physicist and the boundless imagination of the artist, working in concert to turn data into understanding and understanding into wonder. Yet for all we have learned, this story is far from complete. The precise orbital dance of the mice is not a closed chapter, but a prologue to an even grander narrative. one that will be written by the next generation of telescopes, supercomputers, and brilliant theoretical leaps. Our current understanding is a magnificent foundation, but it is a foundation upon which we are only just beginning to build, with new tools set to pry open windows into realms of physics we can currently only dream of exploring. The journey to map the hidden architecture of the cosmos is accelerating, and the coming decades promise to transform our comprehension of gravity, dark matter, and the very fabric of space-time itself, all through the continued study of these celestial motions. Leading this charge into the unknown is a fleet of revolutionary new observatories, both on the ground and in space. The Nancy Grace Roman Space Telescope, slated for launch later this decade, is poised to become a powerhouse for galactic demography. While Hubble gave us breathtakingly detailed portraits of a few dozen interacting systems, Roman will conduct a vast, systematic census, mapping the positions and shapes of billions of galaxies across cosmic time. This enormous statistical sample will be a goldmine. For the first time, we won't have to rely on a handful of beautiful, nearby examples like the mice. We will be able to see the full spectrum of galactic encounters, from the most common to the most bizarre, and understand how their outcomes depend on mass, environment, and the age of the universe. Roman will allow us to watch the cosmic dance evolve over billions of years, providing the observational backbone to test our simulations against the true history of the universe, rather than just a few isolated snapshots. But to truly push the boundaries, we must move beyond the physics of Einstein and Newton and begin to grapple with the quantum realm. At the most extreme scales, around the event horizons of supermassive black holes, the smooth, geometric picture of gravity warping spacetime may begin to break down, requiring a theory of quantum gravity to describe what happens. Advanced simulations are now beginning to tentatively incorporate these effects, trying to model how the bizarre, fuzzy nature of reality at the smallest scales might influence the orbits of stars and gas in these most violent environments. This is not just an academic exercise, it is a direct probe into the most fundamental laws of nature. By creating precise models of the flares of light and gravitational waves emitted by material on the very brink of a black hole, and then comparing those predictions to actual observations from instruments like the Event Horizon Telescope, we might finally find the fingerprints of quantum gravity, a discovery that would revolutionize physics. A key frontier in this quest is the detailed mapping of dark matter. While we know it dominates the mass of galaxies, its true distribution on small scales remains a frustrating mystery. Theoreticians like Dr. Priyamvada Natarajan at Yale University are at the forefront of using gravitational lensing in novel ways to solve this. Her work involves creating incredibly detailed predictions for how the subtle clumpiness of dark matter halos should distort the light from background galaxies. The powerful James Webb Space Telescope, with its exquisite resolution, is now providing the data to test these predictions. By comparing the actual distorted shapes of millions of faraway galaxies to the distortions predicted by different dark matter models, we can perform a cosmic autopsy, determining whether dark matter is cold, warm, or something even more exotic. This will directly impact our orbital models. The precise gravitational field that guides two galaxies together is dictated by the dark matter's properties, so solving its mystery is the key to perfectly predicting the cosmic dance. Perhaps the most thrilling new window on the universe will be opened not by light, but by ripples in spacetime itself. The upcoming Laser Interferometer Space Antenna, or LISA, is a revolutionary mission that will consist of 3 spacecraft flying in a precise triangular formation, trailing behind Earth in its orbit around the Sun. LISA is designed to detect low-frequency gravitational waves, the very ripples produced by the final, in-spiral merger of supermassive black holes. This is the ultimate validation of our orbital models. Our simulations predict that the precise decay of a galactic orbit should end with the black holes at the centers merging. LISA will allow us to literally hear that final, cataclysmic moment, the crescendo of a gravitational wave signal that has been building for hundreds of millions of years. It will transform the field from one of silent observation to one of multi-messenger astrophysics, where we can watch the event with light and listen to it with gravity, giving us a complete and unprecedented understanding of the merger process. Looking even further ahead, the ultimate goal is to use these precise orbits as a time machine to witness the very formation of the first galaxies. In the early universe, before the majestic spirals and ellipticals we see today even existed, the first clumps of dark matter and gas began to merge in a chaotic, frenetic period of building. The orbits within these proto-galactic halos were likely far more chaotic, governed by a denser, more turbulent environment. By pushing the James Webb and Roman telescopes to their absolute limits, we hope to catch glimpses of these infant systems, to see the very first orbital dances that set the stage for everything that followed. This forward-looking perspective is incredibly humbling. It shows that our current understanding, as sophisticated as it seems, is merely the first rough sketch of a masterpiece we are only beginning to perceive. Each new tool, each new discovery, doesn't provide final answers so much as it reveals a new, deeper layer of questions, ensuring that our voyage to understand the precise rhythms of the cosmos will continue to captivate and inspire for generations to come. Now, this entire journey through the cosmos is a story we're telling together, and the most fascinating stories are never a monologue, they're a conversation. So let's pause the narrative for a moment and turn the microphone over to you. After all, the most profound questions in astronomy don't always have a single, definitive answer. They live in the spaces between what we know and what we wonder, and that's where your perspective becomes a vital part of the discovery. Imagine you're the scientist looking at this data for the first time. What's your take? Do you think the breathtaking precision we see in an orbit like this is ultimately driven by cold, hard, immutable math, a universe that operates like a perfect, predetermined clock? Or is there an element of profound mystery at play, a layer of chaos and complexity that we might never fully untangle, reminding us that for all our equations, the cosmos still holds deep secrets? This isn't a quiz, there's no right or wrong answer. It's a philosophical fork in the road, and your instinct tells us something valuable about how we all relate to the universe's grand design. Drop your thoughts in the comments below. Let's get a real discussion going and see where the collective curiosity of this community leads us. And while you're pondering the nature of reality, let's make a specific prediction. We've seen the two possible futures for our dancing galaxies, a graceful departure or a total merger. So which destiny do you think awaits a pair like the mice? Do they possess just enough kinetic energy to escape their gravitational bond and sail on as separate, scarred entities? Or is their fate already sealed, destined to continue their decaying dance until they collapse into a single, new elliptical galaxy? I've put up a poll right here on the screen. Cast your vote. It's a chance to make your own cosmic forecast. Later, we can even revisit the results and see how the collective wisdom of the audience stacks up against the latest findings from astrophysicists. This turns you from a viewer into an active participant, placing a small but personal bet on the fate of billions of stars. This interactive shift is more than just a fun break in the video. It's a fundamental change in how we experience knowledge together. By inviting you to share your reasoning in the comments, we're building a living transcript of this exploration. Someone might point out a nuance about dark matter's role that I hadn't emphasized enough. Another person might draw a brilliant analogy to something in everyday life that makes the concept click for a dozen others. This shared space becomes a collaborative workshop where your insights become part of the learning process for everyone watching, including me. It transforms a passive viewing experience into a dynamic, community-driven investigation, deepening the connection we all have to the material and to each other. So as we move forward, keep that sense of active curiosity switched on. Think of yourself not just as a student of the cosmos, but as a citizen scientist whose observations and reflections are a genuine contribution to the dialogue. That engagement is the engine of discovery, and it ensures that our journey through the mysteries of space is one we are all taking together, one comment, one poll, and one shared moment of awe at a time. And so we reach the end of our journey, a voyage that began with two distant islands of stars and culminated in a revelation of cosmic harmony. We've witnessed the patient, multi-million-year courtship, the first gentle tugs of gravity that set their fates irrevocably intertwined. We've delved into the hidden mathematics of their dance, the precise orbital parameters of eccentricity and resonance that transformed a potential catastrophe into a masterpiece of gravitational sculpture. We saw how the unseen hand of dark matter carved the very pathways they would follow, and how the rhythmic exchange of energy acted as the engine of their transformation, pulling forth brilliant tidal streams and igniting firestorms of new stars. This was not a story of brutal force, but of impeccable timing and flawless alignment, a single, perfect orbit that, through its patient, metronomic consistency, brought two mighty galaxies to their knees, reshaping them not with a hammer, but with the relentless, gentle pressure of a master's touch. This knowledge does far more than just explain a single celestial event. It fundamentally reframes our entire perception of the cosmos. We often default to seeing the universe as a place of terrifying chaos and random violence, a dark void punctuated by cataclysmic explosions. But the story of this precise orbit reveals a profound and beautiful order underlying it all. It shows us a universe that is not random but rhythmic. Not chaotic but choreographed. The same physical laws that govern a child's swing here on Earth, the conservation of energy, the amplification of resonance, also govern the motion of hundreds of billions of stars. This is a humbling and empowering realization. We live in a knowable universe, a cosmos that operates according to elegant, predictable principles that we are capable of understanding. The chaos is real, but it is merely the surface turbulence on a much deeper, more magnificent ocean of order. Let this understanding change how you see the night sky. The next time you find yourself beneath a canopy of stars, look up not at a static, frozen painting, but as a window into a dynamic, living arena. Those pinpricks of light are not isolated. They are partners in a billion-year gravitational ballet. The faint, fuzzy patch you might glimpse through binoculars, that could be a galactic duo locked in their own slow-motion embrace, their light a messenger from a time when our world was young. The silence of space is an illusion. It is filled with the silent, stately motion of orbits on a scale so grand we can only comprehend it through mathematics and wonder. You are not just looking at a pretty picture, you are witnessing the ongoing evolution of the universe itself, a story of creation, destruction, and rebirth written in the language of gravity and time. This journey through cosmic precision is just one of countless mysteries waiting to be explored. The universe is an endless source of wonder, and every answer we find simply leads to more fascinating questions. What other extraordinary dances are happening in the depths of space? What secrets do the earliest galaxies hold about the birth of the cosmos? The quest to understand is a fundamental part of being human, and it's a quest we can all share. I'd love to hear what captured your imagination the most on this journey. Was it the patient power of tidal forces, the hidden dominance of dark matter, or the mind-bending timescales involved? Share your thoughts and your own sense of wonder in the comments below. Let's continue this conversation together. If you want to join us as we unravel the next great mystery of the universe, make sure to subscribe and hit the bell so you don't miss our next adventure into the unknown. Until then, keep looking up. If this journey through the gravitational ballet of galaxies has sparked your curiosity, you've only just glimpsed the edge of a much larger cosmic stage. To truly dive deeper into these celestial showdowns, we've put together a special playlist dedicated entirely to cosmic collisions, filled with videos that explore everything from the chaotic birth of star clusters to the final, fiery mergers of supermassive black holes. You'll find the link waiting for you in the description below, alongside a curated list of resources and scientific papers if you're feeling particularly adventurous and want to explore the raw data and theories for yourself. Staying on this voyage of discovery with us is simple. Just hit that subscribe button and don't forget to tap the bell icon. That one click ensures you'll be notified the very moment we release our next documentary, so you'll never miss an opportunity to journey with us to the farthest reaches of space and time, unraveling the universe's most tightly held secrets one mystery at a time. Your viewership and engagement are what fuel this entire channel, directly enabling our small team to invest countless hours into research, animation, and crafting these narratives that strive to blend rigorous science with the power of storytelling. But this isn't a one-way transmission. Your voice is a vital part of our mission. The comment section is more than just a space for feedback, it's our communal workshop. Scroll down and tell us what cosmic enigma has been occupying your thoughts lately. Is it the terrifying physics of rogue black holes, the mysterious great attractor pulling entire galaxy clusters toward it, or the search for elusive planet 9 in our own solar system? We read every single comment and actively use your brilliant suggestions to plan our future explorations. This is how we build our collective journey, fueled by the shared wonder of a community of explorers. Together, let's continue pushing the boundaries of what we know, venturing into the magnificent unknown that lies just beyond the light of our nearest